Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! Gravity, gravity, gravity. Gravity makes things fall. But on this episode, I'm doing everything I can to defy gravity.
You win this one, Gravity.
From a hoop glider, to an egg drop, to a hover balloon, it's a gravity-defying dance party. All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. My name is Phil, and today on Science Max, we're going to be looking at gravity. What goes up must come down. Today, gravity is the force that makes things fall towards the ground. But just because it's a force of nature doesn't mean that we have to listen to it. No! Today on Science Max Experiments at Large, we're going to use everything in the power of science to defy gravity. We are going to be making a hoop glider. Now, hoop gliders may not look like much, but they fly just like paper airplanes. Woohoo! And here's how you can make a hoop glider. Here's how you can make a hoop glider all your own. This is what you need. Index cards, scissors, straw, ruler, pencil, and of course, science tape, which is just like regular tape, except you use this kind of tape for science. So, here's how you do it. Take your index card and cut it into 3 equal lengths. Take 2 strips, and you take your science tape, and you tape those 2 strips and make a hoop out of it. And with the small strip, you want to make another hoop. Now, what you want to do is take your straw. Now, this straw has a little scoop at the end, and that's not very aerodynamic, so we're going to get rid of that. Ooh, maybe it was kind of aerodynamic. All right, now that we've got the straw, you have to align the hoop and the straw together. So here's what I like to do. Take some science tape and stick it on the straw, and then align it so that it's perfectly straight, and then stick it on. Look straight to me, all right? The small hoop also has to be perfectly aligned with the first hoop. So again, put the tape on the straw first, then align them up, and then start looking down through it, make sure it's aligned. There. Once you have it all taped together, you're done your hoop glider. And it flies just like a paper airplane. Pew! Awesome. So that's what we're gonna do today. Oh yeah, I gotta clean that up. We're going to max out the hoop glider. I'm gonna go meet Sonia at the Ontario Science Center, and we are going to max out the hoop glider into a giant version. We'll probably have to change the materials we use because, I don't think we can get a straw that big or cardboard, but still, we can figure it out. All right, here I go. Aha!
Oh, hi, Phil. Good. What? Pardon? You want me to help you with an experiment? Okay. All right.
Oh, Sonia, I came in.
Phil,
You came in here? I
Are
came
you
in.
okay? Are you okay?
Yeah, I'm fine. Come on, let me show you. This is what I would like to max out. It was in my pocket when I fell, so
What is that?
It's a hoop glider. It was a hoop glider. So how do we max this out?
First, we're gonna need a larger tube.
To
large
replace
tube.
the straw, yeah.
Exactly, and we're gonna need 2 hoops. So we need something that's flexible that will convert into a hoop.
Okay, that's great. So why don't we get started?
Sounds good.
All right, high fives. You may recognize this. It is a spring. Yes, good for you. But did you know that springs can defy gravity? Whoa! Gravity defy. Gravity defying. Gravity. Look at it fly! Defying. Okay, not exactly, but what if I was to hold the spring like this and let it go? What'll happen? It'll fall. Yes, it'll fall. That is true. But while it's falling, what happens to this end? Does it stay in one place? Does it go up? Or does it go down? Let's find out. I'll bring this in so you can really see it. Okay, ready? Watch close. Did you see? Did you? No? Okay, tell you what. We'll watch it again, this time in slow motion. See? The bottom doesn't move, and here's why. When the top of the spring is released, gravity and the tension of the spring are pulling on it. The bottom of the spring is being pulled down by gravity and up by the tension of the spring. These forces cancel out, stopping the bottom of the spring from falling until the top reaches it. Until there's no more tension, and then the top passes the bottom and the whole thing. That is how it works. But here is the real question. Will it happen differently with a longer spring? Huh? Well, I just happen to have a longer spring! Let's max it out! Bring it. Don't tangle it. So, now that I'm up high on this fire escape, let's test it out. Okay, 3, 2, 1, go! A longer spring still has the same forces working on it. The tension of the spring pulling it up and gravity pulling it down. No matter what size of spring, these forces cancel out for the bottom of the spring until the top meets up with it. So there you go, an almost gravity-defying spring! Hey, there's no door handle on this door. I guess I have to take the stairs. Whoa. Sonia and I are maxing out the hoop glider out of bigger and better materials. This is the largest tube I have, right? A giant ABS pipe and some bendable metal to make into hoops. Then we attach them all together and... Okay, big hoop is done.
And little hoop is also done.
Awesome.
Not bad.
Not bad at all. Super solid.
And that's the thing. We have pretty heavy material, so it might not fly as well as we'd like.
But something heavy can always be good, right?
Oh no.
That's what I'm talking about. See how solid it is?
Pretty
No
solid.
damage whatsoever. You want to test it?
I think we should.
Okay. I'm excited. We take our plastic and metal hoop glider outside to test it and... Ready?
Ready?
1, 2, 3!
Huh.
It didn't really fly, did it? Sonia and I made a very solid design, but the problem with it became pretty obvious. Yeah.
It's just too heavy.
Well, that's what science is. Back to the drawing board. Here's something fun you can do if you ever get your hands on a helium balloon. Now, helium balloons float up, not because they defy gravity, but because they're lighter than air. It's because the heavier air around it actually falls past the balloon, and that ends up pushing the balloon up. But what if this helium balloon wasn't lighter than air or heavier than air? It was exactly the same. This is what I like to do. Just take a helium balloon with a long ribbon and a bunch of paper clips, and adding a little bit of weight every time. And what we want to do is make this balloon neutrally buoyant. That means it won't go up or down, but it will be neutral. You want to check it every once in a while. Let's see, 3 paper clips is clearly not enough. 5 paper clips is, 5 paper clips is pretty close. It still might float down, so you want to take off just a little bit of weight, maybe about there. Watch this. You just take the balloon and you put it somewhere and it stays. It stays put. It doesn't go up. It doesn't go down. It's attached to nothing. Now, let's max it out. I had a big balloon, and it was it had a, oh, there. A giant balloon, and look, it's a great paper towel delivery device. Say, did you want some paper towel? Here you go. Science. Yeah, don't worry about Ramona. Just put them up high. Put them up, yeah, higher. Good. Hey. Grab it. Grab it. Gravity makes things fall. But where do they fall? They fall down. Oh. Towards the center of the Earth. Eh? Gravity. It fell, didn't it? So, the Earth causes gravity, right? Well, yes, gravity. Oh, come on. Everything that has mass has gravity. Gravity. But the Earth has so much mass that the gravity produced by everything else is like nothing. I mean, forget about it. But let's say I was in space with this chicken. I would have gravity, and I could exert a gravitational force on this chicken. And if I get my angles right, I might be able to get the chicken to orbit me, like a moon. Behold, my chicken moon, huh? Gravity. But let's get serious. What causes gravity? We don't know. What we do know is that without gravity, there would be no universe as we know it. No you, no me, no chicken moon. I'd miss my chicken moon. Chicken moon, you what? Gravity. Like it or not, the universe wouldn't exist without it. You like the sign? I'll give you a good deal. Half off.
Back to our hoop glider, which was too heavy.
Here's what I don't get. This is heavy, but I can still pick it up and throw it.
Yeah.
An airplane is way heavier. I could never pick up an airplane, but that can fly.
And that's because airplanes have engines, so it has a constant source of thrust. When we throw it, we just have an initial source of thrust. So we're throwing it, eventually loses its energy, therefore,
It falls to the ground.
it
I
falls.
see.
So we need something that's light
Light
and something that's strong.
and strong. Okay, well, let's see what we can find.
All right.
Sonia and I try a plastic tube and some heavy-duty paper. We make hoops and attach them with some duct tape and run outside to try it out.
Hoop glider dance! Okay, 3, 2, 1.
That's pretty good.
That was
Pretty
amazing.
good.
Let's try that again.
Here we go.
I throw the hoop glider, and although it doesn't keep flying forever, it goes much further than our first version, and also further than I could have just thrown the pipe by itself.
Pretty good.
So we've done a good job of making something that flies. Why don't we make a couple different kinds out of different materials, and we'll see if we can get one that flies even better than this.
I think that's a good idea.
Yeah, okay, let's do it.
Sonia and I have created a pretty good maxed out hoop glider, but we wanted to see if different materials would make an even better one. Sonia made a much lighter version,
This time I used cardboard.
and I
made this!
made a slightly heavier one.
Let's do it.
Okay, 3,
Yeah.
2, 1, go! Not bad. My turn.
Here we go.
Okay. That didn't really go very far at all, did it?
No.
Okay, so now we can measure it against the one that we threw before.
And
to see,
that went pretty far.
This went pretty far to see if we've got a better design here.
Here we go.
Right?
Awesome.
So, heavy one, no. Light one, no. Interesting.
No.
This design seems to be the best one. I keep thinking about how you were talking about thrust.
Yep.
All the thrust that we can put in is just what we can put in with one throw.
Yeah.
What if we could give it more thrust than that?
How can we do that?
I don't know, like some sort of slingshot or something. Like it'd have to be a pretty big slingshot.
A pretty big slingshot.
Do you
But
think
I
we can
think
make
that sounds great, though.
I think we make a big slingshot for this.
Why not?
Okay, high five. Let's do it. This is an egg. eggs do not like to be dropped. Oh, fortunately, we can use the power of science to design something that'll keep the egg safe as it falls. Behold, my egg drop contraptions. The thing I really like about this experiment is there's no wrong way to do this. You can come up with any design you want and see if it works. This one here is a bunch of helium balloons. This structure is just to keep the helium balloons on so the egg can touch down very gently. Here it goes. Whoa. and the egg is unharmed, miraculously sound. That one worked really well. Success. This is a giant helium balloon that I think will work pretty much the same way, because I think this balloon will drop just slowly enough that the egg can actually just touch and nothing will happen. So that didn't work. And then there's this one, which has no slowing at all. It's all designed to just absorb the impact. And the idea is that the cone will crumple and absorb the force when it hits the bottom. Oh, no! Oh, no. I think it would have worked if it hadn't turned in the air, but it did, and, well, I guess the egg is completely broken. So I'd call that one a fail. This one is the parachute. You see the egg has been nestled into this foam container, and this is a parachute that will hopefully slow the egg down. Woo! Uh-oh. Whoa. Over. Good. And that one seemed to work well. Yep, the egg is totally fine. The parachute worked. All right, egg drop experiment, totally fun experiment to do, but the question is, how do we max it out? And the answer is pumpkin drop. Same thing, except with a pumpkin instead of an egg. Come on. Okay. All right, pumpkin drop with everything attached all at once. Okay, here we go. Ready? 1, 2, 3. So what we've learned from this is the heavier something is, the more force is acting on it from gravity, which means the harder it is to slow down when it's falling. Okay, fair enough. You win this one, gravity, but I'll beat you next time. I'm gonna get a broom.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. Delicious. Nothing is more important to have fresh than your seafood. It's what makes the difference between a fresh fish and one that isn't so fresh. If you live by the ocean, you probably know that the water gets high tide and low tide.
Look closely, it's the same location.
Amazing! But did you know that this is caused by the gravity of the moon and the sun? Say this cookie is the Earth, and this little happy fellow is me. Hello! And this string represents the water around the Earth. If we didn't have gravity to worry about, the water would all be equally deep around the Earth. But here comes the moon, this mushroom. Now, the moon has gravity, and that pulls the oceans towards it a little bit, like this. And that creates high tide there, and low tide here, and a little bump of high tide on the other side of the Earth. And as the Earth rotates and I'm on it, I experience low tide and high tide, and low tide and high tide. Very interesting. But there's another factor. The sun, or this lemon. Now, the sun also affects the tides, but not as much as the moon. Now, the sun does not affect the tides as much as the moon because it's much further away, but it still has an effect. If the sun was here, then the tides would be pulled away a little bit like that, and the tides would be less severe. But if the moon and the sun line up, like over here, you'd get a very, very high tide and very, very low tide. So there you are. That's how the tides are affected by the gravity of the moon and the sun. Delicious. I'm Buster Beaker, and thank you for joining me on Cooking with Science.
Our maxed out hoop glider was working pretty well,
That was
Pretty
amazing.
good. Here we go.
but we could only give it so much thrust by throwing it. So we came up with the perfect Science Max solution.
Our giant slingshot.
We pull the bungee cord back and hook it onto our hoop glider.
I am ready to fire. Count me down.
3, 2, launch it! Very nice!
Our slingshot is amazing. By giving the glider more thrust, that is, more energy at the beginning so it's going faster when we launch it, the glider soars through the air and flies a long way.
That was great. So there you go. Giant hoop glider. Yeah, Science Max, experiments at large. Nicely done.
Nice.
What more could you ask for?
Well, my turn.
Hey, see you next time. I'm the marker. Take 8. My goodness.
I play the wobble.
Wobble.
The wobble.
Forgot my line. Forgot my line. Going back down.
Wobble, 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 wobble.
Hello? Hello? Hoop glider central calling. Yes? You were having problems with your hoop glider? Oh, what's wrong with it? Oh, you're using it as a phone? Yes, well, that's your first mistake, yeah. Mm-hmm. Today on Science Max, I forgot to tell you my name. My name is, I'll do it again.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max, experiments at large, is all about light and bending light to your will.
Right? Right?
And challenges me to an ever more tricky game of light manipulation. Plus lasers, periscopes, and what does that have to do with light?
Cut to animation!
Find out on Science Max Experiments at Large.
Greetings, Science Maximites. I'm Phil, and today on Science Max Experiments at Large, we're going to be looking at light. Okay. Just stay. That wasn't supposed to happen. I was supposed to press that button, and there was supposed to be all these lasers and special effects, but it didn't. Well, today on Science Max Experiments at Large, we're not going to be doing one experiment. We're going to be doing a number of small experiments because we are going to do a light manipulation challenge. I'm going to get an expert, and she's going to challenge me to a game of light manipulation because I am the master of light. Oh. Well, at least the green lights are working. And okay, forget it. I'm just gonna turn it back to normal. Come on, turn back to. I'm gonna work on that later. I'm gonna need an expert to help me though. Oh, I know. Anne would be really good at this. It really does look kind of weird in here, doesn't it? Oh well.
You okay?
Hi.
Hi,
Ann.
Phil.
Yeah, I couldn't see what I was doing. Here's your lab coat.
Oh.
Thank you for coming.
Great.
Now, you're from Let's Talk Science, right?
Yes, that's right.
All about science education, just like us. Now, you're going to challenge me to a light manipulation game?
A light manipulation game. I've been working on a series of challenges since last time we talked. Each
Awesome.
a little more difficult than the last.
Well, this is going to be great because I am the light manipulation master.
Okay, well, we'll see about that.
Okay.
Challenge number 1.
Take a seat.
Oh, that's easy enough.
I have written something on the back side of this ball.
Okay.
And I'm going to challenge you to read it.
Okay, well, I'm ready. I might be able to read it from here. Let's see.
All right.
Okay, I see something's written on it, but I can't read what it says.
What if you squint?
It looks like a couple lines, maybe? I can't quite tell.
Any ideas how to solve this challenge, Phil?
And I have to be in this chair?
Well, you can get out of the chair to set up your solution. But
Okay.
when you read what I've written on the ball, you have to be sitting in the chair.
Well, it's light manipulation, right? So wait a minute, I've got flashlights in case the power goes out, so maybe I can use a flashlight. Haha, okay, ready? Pew! Doesn't seem to make it any easier to read. Yeah, I got nothing.
Did you give up already?
No, of course I don't give up.
I told you these were going to be challenging.
This is nothing. I will figure this out. I don't know yet.
You're going to have to get creative.
I don't know yet, but I will think of something.
Okay.
Okay, I will be back. Here, hold the flashlight. Not looking, not looking. I'm gonna go this way.
I'm going to wait right here.
Okay. Have you ever wondered why you end up upside down when you look at yourself in a spoon? It's because of light reflection. Light is made of photons. Let's say that these tennis balls bouncing off this wall are photons of light. Now, when the surface is flat, like a mirror, the photons, they bounce in and straight back out again. But when the surface is curved, the photons don't go straight out, they get reflected. So now, this photon is going over there, and if we had photons on this side, they would I don't even know where those ones are coming from. Then, okay, so we got photons on this side that are going that way, and photons on that side that are going this way. So the top becomes the bottom, and the bottom becomes the top, and that's why you look upside down when you look at yourself in a spoon. Okay, cut to animation, cut to animation!
A lens works by changing the direction of light too. Lenses are made out of curved pieces of glass. When the photons of light pass through the glass, the curved surface makes their paths change. What was only this big before becomes this big when you see it. Lenses are used in microscopes to see things that are really small, or in telescopes to see things that are very far away. Both times they are making something small appear large. Anne has challenged me to figure out how to see a small object far away, and using a lens is my solution.
Check it out. It's a giant magnifying lens, and I'm gonna use it to magnify the ball so that I can see it.
Sounds great.
All right.
I set the lens in front of the ball, which Anne has turned so I can't see what's on it. I add a light,
Shine it on the ball so that it's a little bit better illuminated.
and then sit in the chair and ask Anne to move it so it's aligned.
All right, so bring it to your left. Yeah, keep going, keep going. Keep going, right about there. Try bringing it closer to the ball. Okay, wait, that makes it smaller. Bring the lens away from the ball. Ooh, wait. Try a little bit further. Ooh, ho, ho, ho.
You're ready for me to spin the ball around?
Yep.
Okay.
It says 71.
Nicely done.
Easy. Solved.
Wait.
What?
That was just the warm-up.
Oh, yeah?
Yep. You ready for challenge number 2?
Challenge number 2!
I've got another ball.
Okay.
Something else written on it.
Wait. Are you coming back?
Nope.
Huh. But I can't even see you from here. Like how am I? Huh.
You're gonna have to manipulate the light.
I have to see around a corner? I have to see around a corner. All right. I'll think of something. So you remember the tennis balls in the wall, right? Right? Okay, so the tennis balls are photons, what light is made out of, and the wall is a mirror. Now, right now, the photons are hitting the mirror and bouncing directly back. But what happens if they come in at an angle? Like this. Aha! Those photons are reflecting off the mirror and going that way, which means if I want to see what's emitting those photons, I can see it from here. The same thing happens when you look in a mirror. Oh, okay, mirror. Whoa. The mirror reflects the photons over here. I can see the tennis ball launcher in the mirror, which means if there was a barrier, between me and the tennis ball launcher, I can still use a mirror And the photons would reflect off the mirror and come straight to me, which is how you can use a mirror to see around a corner. In fact, periscopes work the same way. Let's make a periscope right now. Hey, it's dark in here. Oh, right, because I'm gonna show you my laser. So the light from my laser bounces off this mirror in a straight line. Haha, reflection. We can use the power of reflection to make the light go where we want it to. We're gonna build a periscope.
Submarines use periscopes because it's hard to see when you're underwater. A submarine will extend a periscope up above the water. The image up here gets transmitted down here. So someone looking through the periscope underwater can see what's going on up on the surface.
And here's what you need to build it. 2 cartons of milk, 2 small hand mirrors, scissors or a craft knife, a pencil, and science tape, which is the same as regular tape, except you use it for science. And remember, if I go too fast, you can always find these instructions on our website. Step 1, cut the tops off your milk cartons.
Take your mirror and trace out a rectangle as wide as the mirror, then cut it out. Put some science tape on your mirror and stick it in the carton at an angle. Then put a piece of tape on the inside. Then,
Get the other milk carton and do the same thing. Put a mirror on the inside and then stack the milk cartons together. But don't stack them with the holes on the same side. Make sure you stack them with the holes on opposite sides. And here is what's going on inside. You've got your 2 mirrors, and one is angled like that, and the other one is angled like this. Light from what you're looking at comes in, hits that first mirror, goes down to that second mirror, and goes to your eye. You can use it to spy on people from below the table. Or from around corners. So there you go. Your very own periscope using light reflection. Did you know that your TV remote can be a flashlight? It's true. If you have the kind of TV remote with a little bulb on the end of it, then when you press the buttons, the bulb lights up. Yeah, I know what you're thinking. You're thinking, Phil, wait a minute. The bulb did not light up, and I've never seen the bulb on my TV remote light up when I press the buttons. Well, that's because your TV remote works on infrared, which is a kind of light you can't see, but you might be able to see it with a camera. If you have a digital camera or a camera on your phone, now you can see. See? It lights up. And because infrared light works the same way as visible light, in that it will bounce off a mirror, here's an experiment you can do at home. Bounce the light off your TV remote off a mirror and turn on and off your television. Check this out. You get a mirror, set it up just right, and then aim the remote at the mirror, and it turns off the television. Pretty cool, right? But now, let's max it out. I've got a complex series of mirrors set up here, and I'm gonna bounce the light from the remote all over the room. And here's what that pattern looks like.
The light from the remote hits this mirror, which reflects to this mirror, which reflects to this mirror, and then this mirror, and then this mirror, and then finally to the television.
Isn't that cool? There you go. Maxed out remote light bouncing infrared flashlight. I gotta come up with a better name, but still, it's pretty cool. Oh, all right. Turn off the television when you leave the room.
I solved Anne's first light challenge, seeing something far away, with a lens.
It says 71!
But now she's moved the ball around a corner, and now I have the solution.
Mirror! A mirror will let me see around the corner.
Clever.
Right? Okay, so all I gotta do is put the mirror in a position sort of like that, I guess, and then I'm gonna sit in the chair. If you could help me adjust that mirror. Keep going that way. Keep going, keep going. Yeah, stop. Nice, okay. Go ahead and flip the ball around and I will read the message. It is too small. I can't, okay, I've solved this problem though. Okay, flip it around. The lens, I need the lens. So we'll use a mirror and the lens to... Good. Yeah. Yeah, okay. I'm gonna sit in the chair. You're in the chair. It is backwards. Oh yeah, a mirror inverts the image, doesn't it? Mm-hmm. That's okay, I can solve this. All I need, whoa! Other mirror is all I need to solve this problem. So if I take this mirror and I put it here, let's see, there it is. It says 42.
Nicely done.
I
Nicely
am
done.
ready for anything. What do you got planned for the hardest challenge?
Are you sure you're ready for this?
Totally.
Challenge number 3.
Challenge number 3 starts now.
What? Wait. No. This is a light challenge. How am I supposed to do a light challenge if it's dark?
You have to get creative.
But it's dark. Well, okay, no problem. I will think of something. I will be back.
Okay.
Okay, careful.
I'll be waiting. Careful.
So you already know about reflection, right? That's when the beam of light, say from my laser, reflects off this mirror and bounces in a straight line. But check this out. If I don't use the mirror and I shine the laser against the underside of the water, it also reflects, just like a mirror. This is called internal reflection. If I have a stream of water and I put my laser beam into the stream, you can see that the laser bounces around inside the stream of water. It's being internally reflected, and the laser isn't going straight anymore. It's following the stream of water down where the water goes. Internal reflection. Now I know what you're thinking. You're thinking, Phil, how does this affect me in my everyday life? Internal reflection. Who cares? Well, I can tell you why you should care in 2 words. Fiber optic wires. 3 words, fiber optic wires. You see, fiber optics carry information all over the planet. The internet, maybe even your television, travels through fiber optic wires. The good thing is, because of internal reflection, you can bend fiber optic wires any which way or around corners, and the beams of light continue to go straight down inside the wires and get out the other end, making it go where you want it to go. Internal reflection, science.
Back to our light challenge. I've seen something small from far away, seen around corners, but now Anne has turned off the lights. But I have a solution.
Ann? Ann?
Careful.
Okay. Sorry, I forgot how dark it was in here. Okay, I figured it out.
Okay.
I have a flashlight.
No.
So all I need to do...
No. Hold on.
Here.
Hold on.
What?
There's one more rule I didn't tell you.
What's the rule?
You can't use visible light.
How in the world am I gonna do this if I can't use visible light?
It's a challenge.
Wait a minute. Okay, here, hold my flashlight for a second. I'm gonna make a phone call.
Okay.
I think I know what to do. I'll be back. I'll be
Okay.
back.
Oh, careful. Oh.
Oh, hey, good to see you. Speaking of seeing things, let's talk about the rainbow. All the colors of the spectrum organized in a beautiful pattern. But what are the different colors? I mean, what makes them different? Well, it all has to do with the electromagnetic spectrum. This is visible light. All the colors of the rainbow. And take a look at that little black line that goes up and down there. That's the frequency of the light. Light is a wave. You see the wavelength is a little wider out here on the red side, and it's a little closer together here on the violet side? That's because every color of light has a different length of wave, or wavelength. And that is what makes them different when we look at them. But if you think that's all there is to the electromagnetic spectrum, then you're mistaken. So what happens over here on the red side? Does it keep going? Yeah, it does. What?
look, we got infrared here, and then we got microwaves. These are the same kind of waves you use in your oven. And then we got radio waves, which are the same kind of waves you use in your radio. They're all part of the same thing as visible light, huh? Let's take a look at the other end. Remember these short wavelengths over here beside violet? Well, does that keep going? Yeah, if they keep getting shorter, you get ultraviolet, and then X-rays, and then gamma rays, huh? Pretty amazing. And look, it's all connected. From radio waves to gamma rays to visible light in between, it's all frequencies of electromagnetic radiation. How is this staying up? So everything outside of the visible spectrum is invisible, right? Wrong! Ha-ha! Bam! Huh? That is an X-ray, a picture we can take using this part of the spectrum. We can use special cameras to see outside of the visible spectrum. Huh? Huh? Right? Yeah. Okay, you got it. Huh? And look at these. These are night vision goggles. They help you see in the dark. They use part of the spectrum called infrared. For those of you keeping score, that's this part of the spectrum right here. Pretty neat, right? I would sell you these, but they're already spoken for. Oh, here he comes now. Hey, Sal. Hey, how you doing?
You got those goggles I ordered?
Yeah, go ahead, help yourself.
Thanks for putting them aside. Can I put them on my tab?
Yeah, no problem.
All right, thanks, Sal.
Okay, see you later. Nice kid. He's always in a rush, though.
Phil? Is that you?
Yeah,
Do you need the flashlight?
I don't. Turn it off. I can totally make my way over to you. Oh.
I can hear you.
Yeah, I'm right here. Oh, right here.
Hi.
Because I have night vision goggles. Ooh, check it out.
Oh, cool.
Pretty cool, right?
That's awesome.
So here's the spectrum again, and here's visible light. My night vision goggles use infrared, this part of the spectrum here with wavelengths just a little bit longer than the red we can see.
Outside of the visible light spectrum.
All right, I would say that's allowed.
No visible light, and I will see the next ball. Have you got it set up?
I set it up while you were out.
Okay, good. I'm gonna sit in the chair and see if I can see it. Okay, here we go. Oh wow, I can totally see everything.
Can you tell me what the ball says?
It says you win.
Nicely done.
So let's recap. This challenge is the same as the last challenge. The light from the ball was magnified by the lens, sent around a corner by reflecting it off a mirror, and flipped back around by using another mirror. But this time it's dark. So, using infrared light, thanks to my night vision goggles, I was able to see the ball and win the game.
The light manipulation challenge is done. Science Max experiments at large. Time to turn the lights back on.
Yep, absolutely.
Huh.
What did you do back there?
I guess we blew a fuse or something.
Uh-oh.
These are night vision goggles. They use some of they use some things that I cannot pronounce.
Have this container of water.
What?
And I make it stream. But instead of going straight back, they're going.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today we're moving air. We're moving it through a tube to make a stomp rocket, vacuuming it out, turning it into a vortex, and taking it with us underwater. All on this episode of Science Max, experiments at large.
That was amazing! Greetings, Science Maximites. My name is Phil, and it's moving day today on Science Max Experiments at Large. Let's see, where do I put this? This is probably a good spot. Today, we are moving air. You probably don't think that moving air will have a huge effect, but you'd be surprised what you can do by just moving air. But don't worry, we're not just gonna move the air around in boxes. We are going to build a rocket! And this rocket uses the science of stomping on something with your foot. This is a stomp rocket, and it works by stomping on this plastic bottle, and air shoots through this tube and pushes the rocket up into the sky. And here is how you can build one of your very own. And remember, if I go too fast, don't worry, all of the steps are on the website, so you can follow along at your own speed. All you need is a 2-liter plastic bottle, 3 kinds of tape: electrical tape, duct tape, and science tape. Science tape is just the same as invisible tape, but I use this kind of tape for science. Then you want some plumber's tubing and some construction paper to make your actual rocket. First, you want to take your plumber's tubing and cut it into 3 lengths. And when I say you, I mean an adult, because you need to use a saw. So you saw it up into a long piece, a short piece, and an elbow piece. We want to make a long tube at the top, and then we also want to make a tube at the bottom so we can attach our 2-liter bottle to. And there we go. Ta-da! Ready to go. But of course, it doesn't stay up, so we have to attach it to a base. And it will look like this. And you see, it's been attached with duct tape here, and I've used electrical tape, and I've wrapped that part around there. Now, building the rocket.
Wrap the paper around the tube and tape it with your science tape. Tape the top closed so no air escapes. Then cut a semicircle to make the nose cone and 3 hoops for thrusters and tape them to the bottom.
There you go. The rocket fits on the tube just like that. And when you stomp on this bottle, it launches. But here's the most important part. The one most important rule of launching rockets. You shoot rockets outside. Come on. Once you get outside to a nice open area and you bring your safety glasses with you, all you need to do to make the stomp rocket work is, of course, stomp on it. You ready? Here we go. 3, 2, 1. Whoa! You see that? That was amazing. Okay, so this is where we're gonna start with the stomp rocket. I'm gonna meet Chris from Logic's Academy, and he's gonna help me max it out. In fact, he's probably at Science Max headquarters already. I should get over there. Okay, where's the... Oh, there it is. Okay.
How you doing?
It's good to see you.
You too.
Chris is from Logic's Academy, and you guys do in-class robotics workshops, right?
That's right, we do.
Great. Well, I was hoping I could get your expertise to help me max out the stomp rocket.
Yeah, Logix makes one of these. I totally think I can help you with that.
Fantastic. So it works great. I just want to make it bigger, better, more maxed out.
First off, we can start by making this pipe a little bit bigger. So larger pipe, more airflow, bigger launch.
Okay, let's do it. Cool. Moving air isn't that hard, right? I mean, air is super light. How hard can it be to move? Well, here's an experiment you can do that lets you measure how hard it is to move air. So what I'm gonna do is I'm gonna hit the ruler with the broom. It's gonna go over there. I hit it, and it moved, no problem. So we're gonna do it again. Except I'm gonna add just a couple pieces of newspaper. All right, ready? Aha, the ruler broke, because this time I wasn't just moving the ruler, I wasn't just moving the ruler and the newspaper, I had to move the ruler, the newspaper, and all of the air that was on top of the newspaper. And that resistance was enough to break the ruler. Pretty good experiment, right? Let's max it out. I've got more table space, I've got a piece of lumber, and instead of a newspaper, I have a tarp. Now the tarp is very light. It is not the weight of the tarp that is going to be the difference. It is how much air I need to move when I hit this piece of lumber. And I've got a Science Max hammer. So first of all, you're not gonna try this at home, right? Deal? Okay, deal. No trying this at home. Okay, here we go. Moving air, test 2.0. It broke, and it didn't even move. Did you see that? I wonder if we can max this out even more. 2x4, which is much bigger than the piece of wood we used last time, and a sledgehammer. Here we go, moving air experiment 3.0. Wow! Yeah, science. Whoa.
So I've joined Chris from Logic's Academy, and we are maxing out our Stomp rocket. To do that, we're gonna use...
Larger pipe, more airflow, bigger launch.
The theory is that moving a larger volume of air through wider pipes will make our rocket work even better. So, we get to work. This version is built exactly the same. We cut and attach the pipes, a long piece, an elbow, and a short piece, then secure them all down. We attach the plastic water bottle and tape it so it's airtight. And then the only thing to do is make a new rocket that fits over the larger pipe.
Ready to try it?
I'm ready to try it.
All right, let's do it.
Let's go.
1, 2, 3, go! That was amazing!
In the end, though it worked, it wasn't much better than the smaller rocket.
I think we could still do better, right?
Oh, yeah.
This is Science Max, not Science Medium. Right, okay, let's go back to Science Max headquarters. Vacuum sealing. That's what you call it when you take all of the air out of something, often a bag, to seal in the freshness of food. I will demonstrate using this Science Max banana. 100% banana, but with added science.
Not all bananas contain science.
Here's how you can do it at home. Put your food in a bag, seal it most of the way, because we have to take out the air from the bag. And we will do that with a straw. Put a straw inside the bag, and then suck the air out of the bag, and then seal it at the very last second. There, a vacuum-sealed banana. Now, I know it's kind of hard to see that it's been vacuum-sealed because bananas don't really crush much when you take the air out. So I like to use stuff that has a lot of air in it to begin with. In fact, there are special bags that are specifically for vacuum sealing that are supposed to store big and bulky items that have a lot of air in them, like this pillow. See this nozzle right here? It's designed to be used with a vacuum. So, what you do is you put the vacuum on this nozzle, open it up, and then you turn the vacuum on.
Oh. The vacuum is sucking all the air out of the bag, just like we did with the banana. But because the pillow is full of air as well, it starts to shrink and shrink. Then you pull off the vacuum and you tie the seal off, and all right. And ta-da! A vacuum-sealed pillow. Okay, let's max it out. What could possibly be more maxed out than a vacuum-sealed pillow?
Vacuum-sealed fill. Okay, I put plastic bags against the door and then sealed the edges with duct tape. And of course, I didn't put any plastic over my head because you never put your head in a plastic bag, right? Well, let's see if vacuum-sealed fill, it works. Whoa. Hey, it's working! Ha-ha!
The vacuum sucks all the air from the bag, which seals the bag and me in it to the wall. That means
I should be able to knock this milk crate out from under me.
air pressure, or the lack of air pressure, is keeping me sealed to the door.
I'm completely suspended! Uh-oh. I shouldn't have done that. No.
So our larger version of the Stomp rocket worked, but it didn't go as high as the first version. Chris and I see how we can improve the design.
The larger pipe and the larger rocket works really well.
It does work really well. I am afraid, though, that the larger pipe means that the same amount of air is flowing slower out the nozzle than it did before.
Oh, so because we're moving only this much air, it's not going to go as fast because this is a bigger tube.
We need a bigger volume over here to match our larger
So a
nozzle.
bigger bottle.
That's right.
I got a bigger bottle right here. Ha ha! Bigger bottle! So hold that, and then all we have to do is tape the bigger bottle
I'm not sure
on.
if that's gonna...
Yeah, like this.
Still though, I'm afraid...
Yeah,
a
so
little
then
bit.
all I need to do is tape it on.
Chris and I attach a larger bottle to our tube. We just need some risers to adjust the height, then we tape it on and we're good to go. Everything else, including the rocket, stays the same.
I still don't understand how you're gonna step on this one. It's just too stiff.
I have a plan. Ha 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 ha! Sledgehammer! You ready?
Yeah, I'm ready.
Okay. 1, 2, 3! It blew the top off the rocket.
Right off
It
the
also
top.
blew the bottom.
Looks like it's a bit rigid to change its volume so quickly.
So it's kind of a one-time use thing, huh?
I think so.
So why don't we try increasing the volume? Even bigger tube,
Yeah.
even bigger container.
What's bigger than a... That's the biggest bottle they make.
What else holds air?
What about an air mattress?
Do you think we could use an air mattress?
I think we could, yeah, a really big air mattress.
Oh, totally. High five. I love that idea. Moving air is a lot of fun, especially if you use one of these, a vortex cannon. They're pretty impressive and they use some pretty amazing science. I'll show you how to build one. It's pretty simple. All you need is a plastic cup, you want a balloon, something round, an elastic, scissors or a craft knife, and a pen. Here's what you do. Take your balloon and cut it just where it gets wide. You take the mouth of the cup right there, and you have to stretch the balloon over the top. And then you want to put an elastic around it, keep it in place. And this now is a surface on the top, and that's what you're going to use to pull back and create your burst of air. But of course, the air's not going to go anywhere until you make a hole in the bottom. So here's what you do. You take your round thing and draw a circle, and take your craft knife or a scissors and an adult and get them to help you cut out a hole. And when you pull back on the balloon, a burst of air comes through the hole. But the air has an interesting shape. Now, I know what you're thinking. You're thinking, Phil, air is invisible. You can't tell what shape it is. Well, I can show you. Come on. This is my maxed out vortex cannon. It's made out of a garbage can. I've got a hole in here, and this is a shower curtain with a ball that I can get a grip on and pull. And then it shoots forward like this. Now it makes a big puff of air, but again, the air is invisible, so we don't know what shape it is, but I can help with that because I've got this, a fog machine. I fill the inside of the garbage can so we can see what the air is doing when I fire the vortex cannon. Okay, come on over here. Ready? Whoa! Okay, ready? Check it out.
The vortex cannon shapes the air into a ring, called a vortex.
It makes a ring. Well, actually sort of a donut.
Because of its shape, the air in a vortex can move much farther than air that doesn't have a shape.
Vortex cannon. Air that has a shape goes a lot further than air that doesn't have a shape. And it's also way more fun. Woohoo! Little to the left. Little to the left, Ramona. Okay, now that's too far left. I don't know what you think. Oh, hey, I don't suppose you're going on vacation anytime soon. Well, if you haven't decided where, may I suggest underwater. But don't forget to pack the most important thing when you go. Hat? Nah. Ukulele? Nah, forget about it. Oh, chicken? No. Sunscreen? Forget about it. Teddy? No, if you're going underwater, the most important thing you gotta pack is air. You see, human beings have been coming up with ways to go underwater for a long time, but the thing is, you gotta bring air with you because, you know, breathing is good.
Check this out. It's a diving bell. One of the first ways humans used to be able to take air with them when they went underwater. You see, it's a big, heavy bell, and it's lowered from a ship above on a rope. And when it gets lowered into the water, it traps a bubble of air underneath. So you can swim around underwater, but then when you need to breathe again, you don't have to go all the way back up. You just pop under the bell and take another breath. Bells like this were actually much bigger when they used to use them for diving to hold more air. Huh? Ring-a-ding-ding. What do you think? You want this? No? It's okay. I got something else. Hold on. Check this out. It's an old-timey diving suit. Air is pumped in through these hoses here, which means the diver has a constant supply of air, which means he can stay underwater longer. What do you think? Yeah, no? Okay, hold on. I got something else. Yeah. This is it. The ultimate in bringing air with you. The scuba suit. This tank holds compressed air, which means it can carry a lot of air with you, which means you can stay underwater for longer. So I'll tell you what, I'll wrap up all three things. What do you say? Yeah? You'll take them? Okay, great. Let me just wrap them up for you. Come on, Teddy, let's go find the bag.
So our large stomp rocket hasn't worked perfectly. A small bottle didn't move enough air, but our larger bottle was too rigid to stomp. And when I used a sledgehammer, it was so sudden the bottle broke and also blew apart the rocket. Chris and I need a large container of air that is soft enough to change its shape easily. So here's the current plan. An even larger pipe, an even larger rocket, and we use an air mattress. We make 2 holes in the air mattress, one to fill it up with a leaf blower, and the other hole to go out the tube to the rocket. Since an air mattress holds lots of air and is very easy to change the shape by jumping on it, we figure it'll be a great way to get lots of air through the tube to launch our rocket.
Okay, let's do it.
Let's do it.
All right, we're gonna go 1, 2, 3, jump, right?
Okay, yeah.
1, 2, 3.
Being a chef is my absolute passion, and cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello! Welcome to Cooking with Science. I'm Buster Beaker. Whenever friends come over, I like to make my famous potato chip recipe. And look at this bag of potato chips. Quite large, there must be a lot of potato chips in here, right? Well, let's open it. What? This potato chip bag is mostly air. Why do potato chip bags have so much air? Well, to tell you the answer to that, I have to tell you the story of 2 bags of potato chips. Here they are. This one full of air, and this bag of potato chips, there's not much air in it at all. Why don't they make them like this? Well, let's find out. First thing that happens is the potato chip bags come off the conveyor belt at the potato chip factory where they get packed into a crate. Here's a crate here. So let's really stuff them in. And then the crate gets boxed up and shipped off to the store. Oh, it's a bumpy ride to the store today. Now we're at the store, and then you come along. Bags of potato chips. What else should I buy today? Oh, I know. How about a cantaloupe? Very nice. Some apples, yes? And take it home, walk along, and you get to the kitchen, you have a choice. This bag of potato chips, where all the potato chips are light and fluffy, or this bag of potato chips, which is not exciting at all. And that's why potato chip bags have so much air, to protect the potato chips from getting crushed. Speaking of potato chips, time to get back to my recipe. What is it? It's potato chip soup. Well, I'm Buster Beaker, and thanks for joining me on Cooking with Science. Perhaps a little bit more cooking.
Okay, so where were we? Oh, right, our maxed out rocket. A much larger pipe, a large air mattress, and the largest rocket yet. Let's see how it goes.
1, 2, 3, jump. 1, 2, 3. Whoa! Yeah! There he goes. All right, let's do it again.
Okay.
1, 2, 3.
It works amazingly well. The large volume of air Chris and I can move by both jumping on the air mattress gets transferred through the large pipe, and even though it's a giant rocket, it sails higher than any other version.
That was great. That was amazing. All right. There you go. Science Max, experiments at large, moving a lot of air.
That has to be the biggest stomp rocket ever.
Biggest stomp rocket ever. Let's do it again.
Okay.
Okay. Oh, it smells so horrible.
It's a diving bell.
And that didn't work at all. That's acting, my friends. Oh, friend, that is so bad.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! It's time to get stuck on magnets. What's our attraction to magnets? What's their attraction to each other? And can I use magnets to levitate and float in the air? All on this episode of Science Max, experiments at large.
Greetings, Science Maximites. Welcome to Science Max, experiments at large. My name is Phil, and today we're going to be looking at the power of magnets. You see, magnets are fun things to experiment with because they are really, they're really interesting. This magnet that I've got here is a neodymium magnet, or a rare earth magnet. It's one of the strongest magnets you can get. A magnet is an object that is attracted to anything that is ferromagnetic, which is iron, nickel, or cobalt. And magnets are interesting because they have two sides. There are two poles. I'd show you, but I can't get the chain off. Hold on one second. Ha-ha! There are two... Oh, no. There are two poles to every magnet, just like the Earth. There is a North Pole and a South Pole. That's right, the Earth is a giant magnet. So, if you take kitchen magnets, you'll find that there's two different poles. I've written north and south on these ones. They don't normally come like that. If you put the north and the south together, they stick. But if you put the north and north or south and south together, they repel. They repel, see? They don't want to go together at all. And you can force them together if you want, but if you do, they will spring away the second you let them go. Whee! But when magnets repel each other, I find that some of the most interesting stuff. Check this out. This is just a small container, and I've got a magnet in here, and I have a loonie attached to it so that it fits nicely in the container like that. For the top, I've attached two magnets together, and I have another coin on it. And if you put them in there, I've made sure that the two poles repel each other, which means this magnet will just sit there and float. Magnetic levitation. Very interesting. And you can pop the top on that if you want and just carry around a levitating magnet. Now, there's a couple fancier ways you can levitate stuff with magnets. This is just a wooden frame I've made. This is completely not necessary. You can use just about anything in your house. A desk lamp works really well. The important part is I've tied a magnet to the end of this arm here, and this is a bolt, which is attracted to the magnet, but it's got a thread tied to it, so it can't get there. Just far enough that it will actually hang in mid-air. Look at that. It's not attached to anything. It's just being pulled up by the attraction from the magnet. The thing is, as soon as you pull the bolt away far enough, it will lose the attraction and it'll just fall. Very cool. Here's one that's a little bit more complicated, but is also really neat. This one uses disc magnets, which have a circle or a hole in the middle of them here. And you put 2 around a pencil and then 4 more in such a position that you can put the pencil against this wood on the side and it will just levitate on its own. You can even give it a spin. Look at that.
And if you want to make the levitating pencil yourself, there's step-by-step instructions on how to build an easy-peasy version on our website.
Meantime, we are gonna max this out. Magnetic levitation on Science Max Experiments at Large. But you're probably thinking, what are we going to levitate? Well, we're going to levitate me. At least, that's the plan. That's why I'm going to the Center for Skills Development and Training. Come on.
Okay, who turned out the lights? Ow, what was that? Why is this room so small? And only going down to waist level. This is the weirdest room I've ever been in. Where am I? What's going on?
Hey, Matt.
Hi, Phil.
This is Matt. He's from Jobmaster Magnets. Now, you guys use lots of big magnets, right?
That's right, we do.
Awesome. So maybe you could help me max out this.
Wow. You did a great job of building the levitating pencil experiment.
Yeah, so what's going on here exactly?
Well, all magnets have at least a north and a south pole.
Right.
And when you put like poles together, they want to repel.
Oh, okay. So have you ever levitated a person?
Not yet.
Well, let's do it.
All right.
Do you think we can use these?
We can try.
Okay, well, put that one on the ground. And, okay, so north, and I'll put the north one on my foot here. And then if I just step, oh, wait a minute. If I step, stop moving. If I step on the, okay, well, first of all, this magnet keeps sort of moving away from me when I try to push down on it. What do we do? How do we fix this?
Well, we need to keep the magnets in position so that they don't move around when you try to bring them together.
Yeah, because I have to come straight down on it, don't I?
That's right.
So why don't we attach this one to the floor?
Good idea.
And then we'll put a board on this one, and we'll see how it goes.
Perfect.
Okay, let's do it.
All right.
This is a magnet. This is a magnet. This is a magnet. This is a shoe. What's the difference? To know that, you have to know your magnets. This is a donut. It does not stick to this magnet. This is a spoon. It sticks to this magnet. These paper clips stick to this magnet. This shoe does not. So what is attracted to magnets? Only things that are ferromagnetic. Here's the difference. Horseshoe, horseshoe magnet. This one is a magnet. This one is not. But the horseshoe sticks to the horseshoe magnet because this one's a magnet and this one is ferromagnetic. Only things that are ferromagnetic are attracted to magnets. Things that are not attracted to magnets, they're not ferromagnetic. Plastic, banana, mitten, sandwich, magazine. No, but how do you know? Do you go around the world sticking a magnet to every single thing one at a time? Hey, Ma, I need you to come over. I need to see if you're ferromagnetic. No, ferromagnetic. No, you don't need to do that. First of all, only metals are ferromagnetic. So that eliminates all your clothing, your luncheon meats, your magazines, what have you. Everything that's non-metal, you don't need to worry about. Never mind, Ma, it doesn't matter. But this clock is metal. It doesn't stick. Well, not all metals are ferromagnetic. Mainly just the ones with iron, nickel, or cobalt. And there you have it. Now you know your magnets. I hit the phone on the magnet there. Okay, can you hear me, Ma? Hang up the phone. Hang up the phone, Ma.
My first attempt at levitating had the magnet sliding all over. So the plan is to take the bottom magnet and attach it to a big wooden board so it won't go anywhere. Then attach another plank to the top magnet to make it a little easier to stand on.
Okay, that is definitely attached to the floor. Thank you. All right, now, if I just get this lined up. Whoa, look at that. You could totally, oh, wait a minute. Totally. It doesn't want to stay put. Oh, wait a minute. They levitate. Come on. Levitate. Why doesn't it want to stay? It just doesn't. Should I stand on it? Okay, I'll stand on it. Here we go. And. Am I levitating?
No.
No. So why isn't this working?
Well, just like your pencil experiment, we need a shaft through the center to hold the magnets in position.
Oh yeah, maybe we could use like a ring magnet.
Yes.
That like we used with the pencil.
Right.
And
we're gonna need stronger magnets.
we're gonna need stronger magnets. Are the ring magnets strong?
Yes, they can be.
Awesome. All right, let's do it.
All right.
Now it's time for a Science Max quiz. Which one of these things do we have magnetism to thank for? Birds flying south in the winter, music, or a sandwich? If you picked A, you're right. Some birds migrate in the spring and fall using the Earth's magnetic field. Many animals can sense the Earth's magnetic field and use it to navigate. Migrating birds fly hundreds or thousands of kilometers north or south when they migrate in the spring and fall. A compass works the same way, by using magnetism to point to the Earth's magnetic North Pole. But if you picked B, music, you're right! Here's some music. The way you're hearing this music is because the musicians recorded their instruments using microphones, which use magnets. And then the signal was translated by a computer and stored on its hard drive, which uses magnets. Then it was broadcast to your TV and comes out your speakers, which use, you guessed it, magnets. And for those of you who said you have magnetism to thank for your sandwich, well, you're right. You see, you'd probably go to the kitchen to make that sandwich, right? Well, I'm guessing you got all of the tasty ingredients from your refrigerator? Well, it works on electricity, which is produced by magnets. And then there's an electric motor in the fridge that circulates the air and keeps it cool. And guess what? Magnets. And finally, the door on your fridge stays closed because the door has magnets. So there you go. You can thank magnetism for birds flying south, music, and your sandwich. It just goes to show, when you're talking about magnets, everybody wins because magnets are everywhere. This has been a Science Max quiz.
Here's an experiment you can do with a bag of water. Take a sharpened pencil and carefully push it through the bag. If you do it carefully, it won't spill. The reason this works is because the bag is made of polymers, long stretchy chains of molecules, and also because the pressure of the water against the pencil prevents any water from spilling out. Now, we're gonna max it out. This is a very large bag of water, and here I have some very large pencils. You ready? Oh. That's one. That's two. Here we go. Should I go from the bottom? Ta-da! Science! Okay. I know what you want. Like I was saying, science! Turns
Turns out, trying to balance two repelling magnets on top of each other is pretty much impossible. Here's why. This is a magnet, and here is the magnetic field. It's often drawn with lines like this, but actually the magnetic field radiates out in all directions. Really, think of the magnetic field kind of like a ball. When you try to balance another magnet on top of the first magnet, it's about as hard as balancing one ball on top of another ball. So here's the plan. Just like the levitating pencil, we're going to use ring magnets because we can put a shaft through the center of one ring, then drop another ring magnet on the shaft. It will keep them perfectly aligned. Then it's just a matter of putting the bottom magnet on a board to keep it stable and using another board so I can stand on it and ta-da! Magnetic levitation! Or at least that's the plan.
Okay. Board,
Magnets.
magnets. Ooh, look at that. Awesome. And now I'm gonna put the platform on. Nice. I got some weights here. Let's see how this works. Yeah. This is gonna work amazing. All right, think I should try it?
Give it a try.
Okay. Here we go. Yeah! I'm doing it! I'm levitating! What?
Just a little bit.
Oh, really?
Yeah.
So, yeah, what do we do?
We need more power.
More power? I like that idea. How do we give it more power?
More shafts, more magnets.
Okay, sure. Well, why don't we do 1, 2, 3, 4 shafts, and then we'll have magnets on all the shafts.
Great idea.
All right. Let's do it. If you attach something ferromagnetic like this washer to a magnet, not only does it stick, but the magnetic field travels down the metal, making it a magnet too, which means you can stick more and more things to each other, and they will continue to stick until you run out of magnetic field. You can do this yourself at home with anything ferromagnetic. Paper clips work pretty well, or washers like I have, or screws, or bolts, and they'll continue to stick to each other as long as the magnetic field is strong enough. You can see it's getting pretty weak here, and they'll all stay magnetized as long as the first one is still attached to the magnet. But if you want to go even further, all you need to do is keep adding more magnets to reinforce the magnetic field. I've got a few here, like this. Let's get the chain started, like that. And then I've got a magnet attached to this washer, so it will keep the magnetic field strong. And I continue to add one magnet, one washer, and we'll just see how far I can go. You can even sculpt it a little bit. Look at that. And then at the end, a whole bunch of paper clips. Eventually, the weight will make it fall off, but it's a lot of fun to play with magnets and make art. Speaking of art you can make with magnets, you can also make sculptures. When everything sticks to everything else, you can make some pretty fancy designs. This is a rare earth magnet, a very strong one, and a bunch of nuts that I've gotten. And this one here is an electromagnet, but electromagnets are a little different because they need an electric current to work. Check this out. This is sort of a magnet dude with crazy hair. There's an earth magnet here, and this is a giant screw, and these are some metal bits, and then I've got 2 more magnets at the top here to hold on his crazy wire hair. He's got crazy wire hair because he's crazy magnet dude. Now, of course, we couldn't just talk about magnetic sculptures without maxing it out, so let's max it out. This is a bunch of scrap metal from leftover experiments, and I've got a bunch of rare earth magnets, and now I'm gonna max out a magnet sculpture. Let's see. There you go, a maxed out magnet, me! I made this guy out of metal pipes with earth magnets in between, and these are his arms attached, of course, with magnets. His hand, his little metal pieces attached with magnet, steel wool for the hair, and of course, hat non-magnetic. All right, here we go. Ready? Want to see a magic trick? Simple copper tube. Drop things through it. Nothing unusual happens, but watch when I drop a magnet through. What? It's not magic, it's science. Because the magnet creates a magnetic field, when it goes through the tube, the magnetic field repels the magnet upwards. Now, the field isn't perfect, so the magnet doesn't come to a stop, but still, it slows down from a fall to a nice, graceful drop. Take a look from above. Pretty amazing, right? Magnets, not magic, science. So I've managed to levitate on some magnets, but just barely. What Matt and I needed was more power. So instead of having one shaft and one pair of ring magnets, we're going to use a larger board and put a shaft on each corner. Then we'll have 4 times the power because we're using 4 times the magnets. Hopefully this will be strong enough to get me floating on a cushion of magnetic energy. And magnets?
Magnets.
Okay, here we go. This is gonna work great. And top board. Ooh, what do you think?
Looks great.
Yeah. Okay, here we go. Matt?
You're levitating.
I'm levitating! Woohoo! All right. It feels cool. It sort of feels like surfing a little bit. All right, thank you so much, Matt. That was amazing. And there you have it. Science Max, experiments at large, magnetic levitation. You know, I'm surprised we could do an entire episode on magnets, and we never actually got them so close to the camera that the camera went all weird, because cameras and magnets, they don't, oh dear. No, that's okay. I can fix this. If I just maybe, maybe if I put the magnet to the camera again, that would, okay, that's not, that didn't help. Oh, okay, well, thanks very much for watching Science Max, experiments at large, and we'll see you again as soon as we get into the camera. Today, we're gonna be looking at the power of magnets. 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 Wait, okay. This one here is called a neodymium magnet, or a rare earth magnet. It sticks to this magnet. Ramona, the fish fell. Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! This episode of Science Max is all about generating electricity. Where do we get this electricity that we use all the time? We try to generate as much as we can using human power, plus solar energy, tidal energy, wind energy, and more. All you need to do is turn the generator. All on this episode of Science Max Experiments at Large. Greetings, Science Maximites. Take a moment and imagine with me, if you will, a time when the only way to light your house was with candles or oil lamps. There was no electricity. That meant no power tools, no video games, no telephones, and worst of all, no TV. Fortunately, we live in a world of electricity. If you've ever lost power in your city or neighborhood, you know how hard it is to get by without electricity, even for one day. But where does it all come from? Where do we get this electricity that we use all the time? We make it. That's the cool thing. And I can show you how to make it as well. Check it out. All you need is an electric motor. Electric motors are pretty simple. All you do is get a battery and you attach it to the electric motor, and that makes it work. There we go. attached to the battery, it spins. But if you spin the electric motor, it creates electricity. And that's what we're gonna look at today, creating electricity. We're gonna build a wind turbine. But first, you need an electric motor. And you can probably get one from a broken toy. Just make sure that the toy is broken and that the broken part isn't the electric motor.
Here's what you need: index cards or construction paper, scissors, push pins, science tape,
It's the same as invisible tape, except I use this one for science.
a cork, chopsticks, craft sticks, and modeling clay. And remember, all the steps for this experiment are on our website. To begin, cut the index cards into strips and tape down a push pin so it sticks out. Then fold over the index card and tape it together. Then stick the pin into the cork and repeat that step.
If you want as many blades as you can get on your fan, you're welcome to do that.
Next, take your modeling clay and stick the chopsticks in, then tape the craft sticks in between with science tape. Then take the motor and stick the cork on the end, then wedge the motor in between the craft sticks and tape it down so it stays put.
And there you go, a fan that will spin in the wind.
You want to adjust the fan blades so they all face on a bit of an angle. That way they will catch the wind and spin.
There we go. Now when it spins, it will create electricity. I'll show you with this. It's a multimeter. And a multimeter measures little amounts of electric current. There. The hairdryer makes wind, spinning the fan blades, and we are creating electricity. Now, pretty much all electricity that you make comes down to turning a generator. A small motor like this isn't gonna produce a lot of electricity, barely enough to power one tiny little LED, but it's a start. And a good start is all we need, because today on Science Max Experiments at Large, we're gonna look at all kinds of different ways of generating electricity. Plus, I wanna find out just how much electricity one human being can generate. Although one human being is gonna be kinda lonely, I'm gonna need an expert. Oh, I know, Anthony from the Ontario Science Centre. He can help. I wonder if he's busy. Well, come on. Oh, Anthony! Phil? So I was wondering if you could help me with an experiment. I want to generate as much electricity with human power. What do you think?
I think that sounds awesome.
Okay, great. Let's go back to Science Max headquarters.
Is that the portal?
Yeah. Don't worry, all the kinks are worked out. I know what it is. It's this. Where did you end up?
I was in the vents.
Oh, I ended up in the bathroom. All right, well, now that we're here. Okay, so this is what I started with. And this is just, you know, an electric motor, right?
Right.
So you can generate electricity, you spin it, so I figured in order to generate more electricity, you get a bigger generator?
Exactly, yeah. The bigger the generator, the bigger the magnet, the more the copper, the more the electricity.
Oh, well, you know what we should do is we should just get an even bigger one, like a giant one that they use in like at a power plant or something, or?
Not quite. That would be too big for a person to be able to turn. It'd just be impossible.
So you think this is a good size?
I think this is a great size.
Okay, so that's good.
This is called a multimeter. We're gonna hook up the wires. I will do black to black.
Black to black.
To red. And as you turn our generator, we can see just how much electricity we're generating. Okay, so.
Here, you hold on to that.
This,
and
you
I'll
can
turn
start
the
turning
generator.
Now it's time to play How Much Electricity Did They Make?
2.4 volts, yeah, it's not bad.
Oh, 2.4, yeah, it's not great.
That's just enough to power a small LED flashlight. Better keep trying, boys.
I got some handles here that we're going to attach to the
perfect.
end of the generator so
Yeah.
we can spin it.
Okay, let's try.
No matter how fast I cranked the large handle, I couldn't make any more electricity than before.
Okay, let's try something else.
But it's a smaller handle.
Perfect, okay, yeah.
That's good?
Yeah, well, maybe it'll let us get more spins in.
Oh, yeah, because I don't have to make as big a circle.
Exactly. Yeah, it's working already. We're up to like 3.5,
Now, how much electricity is Phil making?
4.5.
That's the same as 3 AA batteries. Maybe enough to power a toy car. Still, a long way to go.
Yeah, it's a lot higher with the faster spins. Oh, all right. You okay?
I'm okay.
Maybe we could use like some gears or something like that.
Oh, yes, you know, that's a good idea because this circle that I'm making here, I can only go so fast. So
Yeah.
maybe with gears, you can do 1 circle here equals like 10 circles on the other gear.
Exactly.
Yeah.
Okay, so kind of like the gears on like a bike.
Yeah, the gears on a bike or something like that. A bike! Of course! Yeah, so we get a bike and we attach the back tire to the generator.
The generator, and then you can use the pedals of the big gear to power the small gears.
Okay, great. We'll go get a bike.
Yeah.
Yeah, high five. All right. Oh, right, they're over here. This is a generator. It generates electricity when you spin it. But how does it work? What wizardry is inside? Well, actually, generating an electric current is fairly simple. All you need is 2 things. First, you need a conductor, like this coil of copper wire, and you need a magnet. Now, this is a galvanometer. It measures small amounts of electric current, and I have my copper wire attached to it. Watch as I put the magnet inside the copper. I get a little bit of an electric current, and then I take it out. It goes in the other direction. A little bit going this way, and then I take it out, a little bit going that way. Positive, negative, positive, negative. This kind of current that goes back and forth is called alternating current, or AC. It's the same kind of electricity you have in your house. But here's the cool thing. Watch this. I put the magnet in and I leave it. It goes back to 0. You only get electricity when you move the magnet. All right, so let's create our generator. Instead of starting with a copper coil like this, what if we just had the magnet and we have it staying still, like that, and we move the conductor past it, like spinning? It's good, but not great, because we're only getting a little bit of electricity as it passes. So let's make it more efficient. Let's put in some more magnets. 1 on either side, and 1 on the top. And now when we spin it, it goes past all of these magnets, and every time we get a little bit of electric current. Well, this is how a generator works. If you take an electric motor or a generator apart, you can see there's a coil of copper wires on the shaft, and it spins around like this. And on the inside, there are magnets. So there you go. When you put it together and spin it, you get an electric current. Or if you put an electric current in it, it will spin, just like an electric motor. And that is how a generator works. Anthony and I are trying to create as much electricity as we can using just human power. But so far, it hasn't been going so well. It all comes down to how fast we can spin the generator.
Maybe we could use like some gears or something like that.
In order to get it spinning really fast, we're gonna use a bike. It's just a matter of getting a bike, taking off the wheel, putting it on a stand. It is now a stationary bike. It'll be even more stationary once we screw it down. And attaching the generator. All right, the bike generator. Bike-orator, what should we call this thing?
Bike-nomator.
Bike-nomator. I like it. So, okay, let's go over what we've got here.
Okay, so we've got 2 gears. We've got a big one, we got a small one. We turn our pedals, and the big gear turns the small one.
So this is the whole point of this build, is so that we can get 1 revolution here means a whole bunch is spinning there.
Exactly. The more we get here, the more our generator spins and the more electricity we get. We get tons.
Awesome. And obviously using bike, because you're using your legs.
The strongest muscles in your body.
Awesome. Okay, so now what's with this horn? That is a loud horn.
I know. I tried to warn you.
That is great. I love that. So Anthony and I hop on and give it a pedal. We pedal as hard as we can, and we produce a pretty good amount of electricity. How much electricity did they produce?
We got up to maybe like 18 there. You did a pretty good job.
That's enough for a power tool, like a drill. It's good. You know what? This works well, I think, for keeping a good number for a long period of time.
Yeah.
So we can get up to like 18, 20, but it doesn't We can't really get any higher than that.
Yeah, you know what we need is like one really hard pull, like all of a sudden. That way you can get like a spike.
Yeah, you're right. So it's like instead of putting all that effort into going for a long time,
Yeah.
you put all the effort into one quick motion.
Exactly.
Yeah, good idea. So you wrap a rope around here and then you just pull it.
Exactly. Exactly.
And that'd be a really fast motion.
Uh-huh.
Spin it really quick and get a very high number.
high spike. Exactly.
Okay. You know, we're gonna have to take the bike apart though.
Okay.
All right. Well, it's science.
Okay, cool. So I'll just get.
Oh, you know what? We actually don't have to take the whole bike apart. We just have to take the generator off.
Oh, right. Okay.
Okay,
Hang
cool.
on a sec. I got it.
And maybe we should attach the horn to the next thing too.
Turn it off.
So you want to generate some electricity. But what do you choose to generate that electricity? Hydro? Nuclear? Coal? Solar? Who knows? I do. I know. And soon, so will you. In order to generate electricity, you need to turn the generator. Turn the generator. One of the most common ways to turn the generator is to use one of these. It's a steam engine. Usually they're a lot bigger. You see, you heat the water to boil it and turn it to steam, which works a piston, which turns the generator. Huh? Pretty amazing, right? But what it really boils down to is heating water to make steam. Boil water to make steam to turn the generator. Coal power. Burn the coal to boil water to make steam to turn the generator. Natural gas. That's different, right? Nope. Burn the gas to boil water to make steam to turn the generator. Nuclear power. That's different, right? Nope. It creates heat, which you use to boil water to make steam to turn the generator. Wind power. We don't even need heat for that. Just use the wind to spin the fan to turn the generator. Hydropower. Just pour water across something that spins to turn the generator. No matter what, making electricity always comes down to turning the generator. It's always yada yada, yada yada, turn the generator. Except for solar. Solar does not work like that. But other than that, it's always yada yada, yada yada to turn the generator. And now you know your electricity generation. Hey, Ramona, you wanna come and give me a hand over here? My arm is getting tired.
Whew, it is hot out here. Oh, in order to generate electricity, you need to spin a generator. Most forms of electricity generation work like that, but not solar. Solar panels like this one generate electricity from the sun's energy. So, how do they do it? Well, this is a solar panel. Okay, it's not really a solar panel, I just sort of put this together, but it works the same way. There are two plates, and on these plates are electrons. I've got golf ball electrons up here, ping pong ball electrons down here, but they're all the same thing. Now, this happy little fellow is a photon, energy from the sun in handy-dandy particle form. What happens is photons come from the sun and hit the top plate and knock some electrons from one side to the other, like this. And that knocks over some electrons. Now, these extra electrons travel up a wire in the form of electricity, and we can use them to do work for us. Then they change to the other charge, go back, and we start the process all over again. That is how solar panels work. But remember, it only works when there's sun and photons.
Anthony and I are trying to generate electricity using human power. Spinning the generator didn't work too well, but we found if we used some gears, like those on a bike, it worked better.
You know what we need is like one really hard pull, like all of a sudden.
Using gears is a great way to get work done. The good news is there are generators with gears already in them. That means if we can turn the spindle once, the gears inside will spin the coil a lot of times. The only downside
turning the spindle gets harder the higher the gear. Anthony and I attach a spindle and then we wind up the rope, which takes a while.
Okay, so the plan is, it's on a big spool now.
Yeah.
And you just run as fast as you can.
Got it.
And we'll hopefully get as many revolutions as we can, depending on how fast your top speed is.
Okay.
Sounds good?
Sounds good. I can be pretty quick.
Okay, good. All right.
Ready?
On your mark.
Uh-huh.
Get set. Go.
How much electricity did they create? 24 volts.
Actually, not bad.
That's enough to power their own personal scooter. Not too shabby, boys.
We need like a hard pull all at once.
Yeah. Something like really big. So what if we could get like really high? Like, like up there. Could we attach the generator up there? You could jump down from there.
And I would hang on the rope?
Yeah.
Yeah, it's good, but I don't want to jump from up there. Oh, what if we put a pulley up there?
That would
then
work.
the rope goes through the pulley and then back down, and then I jump from somewhere much safer, like just on top of here onto a crash mat or something.
That sounds great.
And that's my full body weight on the rope.
That sounds great.
All right, high fives.
Yeah.
Tidal power in 60 seconds.
By now you know that in order to create electricity, you need to spin a generator. Scientists and engineers are always coming up with lots of new ways to use natural forces of the Earth to spin a generator and create electricity. One of those natural forces is the power of the tides. You see, the water in the oceans doesn't stay still. Every few hours, the water, or the tide, goes out. And then a few hours later, it comes back in. So, if you attach a paddle wheel in the water and attach that to a generator, when the tide goes out, it creates electricity. When the tide comes back in, it creates electricity. That is how you create electricity using the power of the tides. It's water power. In fact, hydroelectricity is also using water power. Do we have time to talk about We don't have time? We don't. Okay, maybe come back.
Hydroelectric power in 20 seconds.
20 seconds? Okay, hydroelectricity comes from water. Hydro means water. So all you have to do is find a place where water pours down from a height. And you can put a generator in there, and ta-da, you're creating electricity with the power of hydro. Ha 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 ha! I did it.
Anthony and I have pulled and pedaled, and now we're going to hang on to the rope and use our whole body weight to spin the generator as fast as possible.
Okay.
Okay.
Crash mat. Let me test it out.
Looks good.
Yep, it's good for crashing. So I go up here. Okay, I go up here.
Climb on up. We'll get you the rope. Got your helmet for safety.
Helmet for safety, crash mat for safety. So we have the rope, and it goes up through that pulley, and then back down to our generator with a spindle on it. And as I fall, the spindle will turn.
Exactly.
And hopefully the speed of me falling and holding and yanking it down as hard as I can will be the biggest spike of electricity yet.
That's right. We'll be measuring it on our multimeter here.
Okay.
Okay.
Ready?
You ready?
Yeah.
Here we go. 3, 2, 1.
I jump down and my whole body weight pulls on the line.
Oh, that was awesome. That was like our biggest spike ever. That was amazing.
All right, high fives. Biggest spike ever. Is it enough to power my house?
Nope.
How much electricity did Phil generate? Almost 30 volts. How much does he need to power his house? 120 volts. He's still off by quite a bit.
Well, we've learned something. Nuclear,
Wind,
hydro,
solar,
natural gas,
coal power.
It's all great ways to generate electricity.
Yeah.
And human power,
Not so much.
not as good. But human power is more fun.
Yeah, way more fun.
Yeah, so your turn?
Yes!
Okay.
Give me,
You take the helmet and I'll take the multimeter.
Okay.
And then we'll go and we'll do it again. Okay. Wait, I gotta wind it up.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
So this is a solar panel, and this is a train. You're generating electricity. You're in the way of my solar panel.
Oh, no, it's spinning the other way. I forgot a step. I forgot a step. The water in the oceans doesn't stay still. The thing in the background, it totally threw me off. What was that?
Okay. Where were we? We were...
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max Experiments at Large. Science Max! Today, Science Max is all about sound. We bend the power of sound to our will by making the loudest sound we can.
Wait a minute, a subwoofer.
Make cornstarch mud dance, glasses break, and things vibrate. It's the sounds of science. Today on Science Max Experiments at Large.
Greetings, Science Maximites, and welcome to... Can you hear me? Greetings, Science Max! You can't... hold on a second.
Greetings, Science... Yeah, that's much better. Greetings, Science Maximites, and welcome to Science Max Experiments at Large. Today, we're going to be talking about sound. Sound is all around us. We use it every day, but what is it really? Sound is energy. Let's say that this is the... No, stay. Stay. Okay. That this spring is the sound of my voice. When I make noise, it travels away from me in a wave. One air molecule vibrates the next, air molecule vibrates the next, and it looks like a wave. And when there's a little bit of energy, the wave doesn't move very much. Science. But when there's a lot of energy, the wave moves a lot. Science! What do we do? What do we do to make sound louder? This is the Science Max theme song. But it's not very loud because the speaker on my phone isn't designed to make super loud noises. So what we're going to do is find ways to make the volume of that song as loud as possible. Here is one way. Take a phone playing some music and put it in a glass. Make sure the glass is empty, of course. Huh? And suddenly, it's a lot louder. Wow! Why this works is one of the things we're going to be looking at today. So that's what we're going to do today on Science Max Experiments at Large. We're going to learn how to make sound louder, as loud as we can. But I'm going to need an expert to help me. Oh, I know, Michaela from the Ontario Science Centre. She's very smart. All I need to do is go to the Ontario Science Centre and see if she's busy.
Are you okay?
Yeah, Michaela, it's good to see you.
Nice to see you too.
That was weird. I was wondering if you could give me a hand with an experiment.
Oh, I'd love to, yeah.
It's a sound experiment.
Sounds awesome.
Right on. Okay, we'll take the portal. We'll go back to Science Max headquarters.
Oh, take the portal? Cool.
Haven't you taken the portal before?
No, don't you remember? It wasn't working last time.
Oh, well, it's
Is it working?
fixed this time. Yeah, no, it'll be great. Trust me. Here we go.
Whoa. What's going on, Phil? Is everything okay?
Usually when I come through the portal, I land on something or something falls on me or...
Not today. It's your lucky day.
I guess so.
Safe landing.
Safe landing. High five. All right, so let's get started.
Okay, cool.
This is the experiment I want to max out today, Michaela. I know. Pretty impressive, right? No, hold on.
Okay.
So I take my phone and I play some music on my phone and it's louder. right?
Check it out. Now, you've just made yourself a resonance chamber.
A resonance chamber.
A
Very
resonance
nice.
chamber is what we say when we're trying to describe how the sound is amplified. So if the sound's coming in from one direction, it's bouncing around, not really losing energy. So when more sound comes in, that's amplified. We hear it a lot louder.
That's cool. So that's what I want to do. Hold on, let me turn this up. That's what I want to do today. I want to max out as much sound as we can get out of the Science Max theme song, which
I'm
is
so excited.
totally awesome. So what else can we do to do that?
Well, there's a couple avenues I'm thinking. Do you want to try something with electricity or without electricity?
That's because with electricity, we're talking speaker systems and
Yeah.
Right. So
We
why
can
don't we
get it.
do no electricity for now, and then
All
we
right.
can jump to electricity when we feel we've exhausted everything that's non-electric.
Cool. So I was thinking we could try to make a megaphone, because if we have a lot of sound, we could, funnel it in one direction, and then it would be louder.
Okay.
What do you
Yeah. So
think?
the megaphone's pretty easy to make, right? We could just use. In fact, we could use this piece of paper, right?
Yeah, let's try it. What do you think?
I think it's very megaphony. Science taping it up. Okay, ready? Okay, turn it on. Play it. And doesn't sound, but what if I do this?
Hey, there it is. Right on.
Oh,
That song.
yeah? You hear it?
Yeah. Oh, I hear it.
Okay. So that worked pretty well. So,
Yeah, it works. Works well.
so this is pretty easy, right?
Yeah.
Megaphone?
Oh, yeah.
So why don't we max this out? Why don't we make a giant megaphone and see if it makes a big difference?
I think it will. Let's do it.
Sounds good. Let's get started. All sound is vibration, but it's really hard to learn about that vibration if you can't see it. I mean, sound is invisible, right? Well, here's a way that you can make sound visible. All you need is some plastic wrap and salt and a bowl, just a regular bowl, and an elastic like this. So what you do is you take the plastic wrap and cut off a piece just large enough to fit over the bowl, and then use the elastic to wrap around the bowl to keep the plastic tight. Pour some salt on the bowl, and then watch this. Hello, vibrating salt. The plastic wrap is stretched tight over the bowl, making it like a drum. A drum that's very sensitive to sound vibrations. Your ear works the same way. That's why we call it an ear drum. The vibrations from my voice make the plastic wrap vibrate, and that makes the salt dance. But there's more. Let's max this out. This is a Chladni plate, and what it is just a piece of metal on a platform that vibrates up and down to a frequency which I can program with this dial here. And when the sound waves vibrate the plate, they can interact in ways that make the sand form interesting patterns. Take a look. The sounds I'm generating vibrate the plate, make it move like a wave. But when the vibrations reach the edge of the plate, they bounce back and interact with the other waves going the other way. The way these waves interact at different notes is what causes the sand to make these different shapes. So this is great, but you know what? We can max it out even more. Maxing it out even more. Okay, that's about as much as I can take of that. So Michaela and I are on a quest to make the loudest sound we can. The first step is to make things louder without using electricity. We've looked at a resonance chamber, and now we're going to make a large megaphone. Sounds can be amplified by bouncing sound waves around in a space. When I put my phone into the glass acts as a resonance chamber. The sound waves bounce around inside the glass, and they combine and stack on top of each other. This makes the sound louder. Resonance chambers are used by musical instruments like an acoustic guitar. The wooden chamber bounces the sound waves around, and the sound waves build on each other to make the sound louder. A megaphone bounces sound waves as well. Instead of going off in all directions, a megaphone makes the sound waves all go in one direction. That's one of the reasons why a megaphone makes sounds louder, but only when it's pointed at you.
So will a bigger megaphone work better?
So we've made a larger megaphone, which is exactly the same thing. You just take a sheet and you roll it up, except our sheet was plexiglass covered in paper, and we've taped it together so it stays. And the idea here...
Oh yeah, bigger megaphone. We're gonna vibrate even more of the air inside of here, and hopefully this thing will be louder.
Okay, so you're ready to try it with the phone?
Yeah.
I think first we should try it with our voices, though.
Okay.
Now, what's your favorite season?
Awesome, I can totally hear you. That's amazing. And it would be fall. No, summer. Spring?
Think
It's
better.
anything but winter.
So the maxed out megaphone worked, but we still had to try it with my phone.
Okay.
All right.
Yeah?
Oh yeah. Oh, definitely.
How about now?
No, not so much. Not so much. Oh yeah. Nope. Nope.
So that is a
That was
great
cool.
example of non-electrical amplification.
That's right.
Amplified the sounds, no electricity. Okay, bye-bye. All right.
Come on, make some noise! Well, how do you make noise? Well, to know that, you gotta know your sound. All sound is vibration. Here, take a closer look. You see? You got... Okay, let's try this again. All sound is vibration. The string of this guitar vibrates, which vibrates the air around it, causing the sound that you hear. Your vocal cords vibrate in your throat, causing you to make a sound. Ah, 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 la, 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 la. Look at this thing. Look at this thing. See how it's shaking back and forth? It's vibrating. Things that make a high sound, they vibrate faster. Vibrating really fast. Things that make a low sound, vibrate slowly. High note, vibrating fast. Fast! That's vibrating. And now you know your sound.
Everything has a resonance, a note that it vibrates best at. Let's say this fish tank is, well, any container where sound would be vibrating, and the waves of water are actually waves of sound. Now, normally, sound waves will bounce around inside the container, off the walls, and go back and forth like that. And how fast I move this piece of wood is the frequency, or the note, that we're playing. I could vibrate this wood very fast and make a high note. I could move this plank very slow and make a low note. And the waves just bounce around inside the container. But there's a speed I can move this plank where the waves stop going side to side and suddenly get twice as big.
The waves bouncing off the sides of the tank are meeting the waves going in the other direction. But what we end up seeing is peaks of the waves not moving side to side, just going up and down, like you see here.
This is the resonant frequency of this container. So, let's max this out. Say I have a wine glass, and I wet my finger and I rub it around the rim. It vibrates at a certain note. That note is the resonant frequency of this wine glass. So what would happen if we were to play that note back to this wine glass really, really loud?
And yes, this is something you should not try at home.
This note makes the glass vibrate the most.
Finding the perfect note things vibrate best at is great for musical instruments, but it's not great for this wine glass. The sound waves are causing the glass to vibrate a lot. And because this glass is delicate, it can only vibrate so much before it breaks.
vibrations were so strong that the glass literally shook itself to pieces. Science! Sorry. Science! Oh, wait. Science!
Michaela and I have tried a resonance chamber and a giant megaphone to make sound louder. Now it's time to move on to the next step of the plan, using electricity to help us amplify sound. And that means speakers!
So, speakers that you have at home, 3 different speakers here, right?
Looks
3
really
different
busy.
cones.
Yeah, there's a lot going on.
So, what's the deal?
Well, here at the bottom, we have a subwoofer.
Wait a minute, a subwoofer.
Subwoofer.
So it's a woofer? The word is woofer?
Yep.
And it's, okay, so it's for dogs. Right?
No, a subwoofer is for low notes here in our speakers.
Ah.
At the top here, we have a tweeter.
So it's for birds. It's birds, dogs. So let me guess, low notes?
Yeah.
Tweeters, high notes?
Yeah, high notes. And then we have this guy here in the middle, and that's called your mid-range speaker.
Oh, that's not nearly a cool name. Now we have speakers, we've taken a look at that, but why don't we take one apart,
Cool.
right?
Yeah,
Because
let's do it.
I've got this one here that I spilled juice on, so it doesn't work anymore. So I've kind of taken it apart. So
Cool.
it's got,
Man, that's awesome.
okay, so it's got the cover. That's cool. So what I find interesting is there's the speaker and the wires, right? Because it's electrical amplification. But check this out. This is just a ring to hold that on. And the rest is just an empty box.
We know what that is. Resonance chamber.
That's right. So that's why it's an empty box. So
Let's take this apart too, see what's going on.
So that's the paper cone, right? So that's that's the drum, I guess. It's like the eardrum, the thing that vibrates.
Yes, yeah. This whole thing vibrates.
So this whole thing.
That's for electromagnet. When we turn this on, the electromagnet goes on and off, and it's causing this whole thing to vibrate.
So that's how it works. It's the electricity turning the electromagnet on and off.
Exactly.
And it's on and off and on and off and on and off and on and off. And then it makes it vibrate at certain speeds, right? Hertz. The number of times it vibrates per second is hertz. What we could do is we could max it out with the speaker and plug the phone into speaker. But this step does not feel like Science Max to me because anybody can do that, right?
Yeah.
You can just turn up your television right now, and that's pretty much the same kind of thing. We need electrical amplification, but maxed out.
Max it up. What are you thinking?
Okay, so I've got a friend, and he's got a stereo system that he built, he put together, and what he does is he tours different cities. So he said he'd bring it by Science Max headquarters.
He's gonna bring it here?
We gotta go outside.
We can see this thing.
And it's very loud, so we have to go outside.
When's he coming?
Right now. All right, let's go check it out.
Seeing sound vibrations is fun.
This kind of speaker is a special kind. It's called a subwoofer, which is designed to give you the low notes, the big rumbly bass sounds.
I tilt the speaker so it's facing up and cover it with big sheets of plastic wrap, which I push into the cone. Then, tape it so it's nice and secure.
Then, what you need is some cornstarch mud, which is 2 parts cornstarch, 1 part water.
I've got some yellow cornstarch and some blue cornstarch.
This experiment works the best with low notes.
I'm playing a tone through the stereo that is very low. Here's what happens when I turn up the volume.
It's alive! You see, cornstarch mud is a shear thickening fluid, which means when you impact it, it turns solid. So the vibrations from the speaker cone are making the cornstarch mud impact, and that's turning it into a solid. But then it sort of also melts back into a liquid, so you get little columns of cornstarch coming up and falling down again. It's like it's dancing. Whoa! Visual sound waves. Science!
So Michaela and I are going to max out sound. To do that, we need a maxed out sound system.
This is gonna be amazing. This is gonna be super maxed out sound experiment. This is James, Michaela.
Hey, James, how are you?
Thanks for coming, buddy. Nice to meet you. So, tell us about your speaker
speaker system. It looks a lot like a vehicle.
This is my audio van. It's got 4 15-inch subwoofers in the back. It's got a whole bunch of power to power it, and I'm glad to be here to let you guys hear it today.
Awesome. So if I have a speaker at home, like a little speaker like this, how many watts do you think that would be?
Somewhere between 15 and 25.
15 and 25 watts.
Yes.
And you've got 4,000.
Yes.
So that's a lot more.
Yeah, quite a bit.
And subwoofers, they play low notes.
Yes.
So is that better when you have a van like this?
With a car audio van like this, you want to play low notes, like your house stereos, and that will play anything from 120 to 200 hertz. I'm playing 20 hertz to about 35 max for you guys today.
So that's like a sort of rumble of thunder,
very
kind
low.
of blah, blah, blah,
Yeah.
where you really feel it, like a train going past almost.
Oh, that's cool.
So we get our hearing protection on and we try it out. I know what you're thinking. Phil, what's the point of having loud music if you can't really hear it? Because we've gone from listening to music to feeling it. The sound waves are so strong that they have become a physical presence. Michaela's hair flies around because the air from the speakers is creating shock waves. The sound waves are so powerful, they move the air back and forth, which makes Michaela's hair dance all over the place. And my hair, not so much.
I'm totally jealous of your long hair.
Yeah, you need to get longer hair.
Okay, hold on. I'll go right.
Okay.
Whoa! Science Max, experiments at large, super sound! High fives.
Yeah.
Okay, ready to go again?
So cool. Yeah, let's do it.
Okay, here we go.
At the bottom.
I can't reach it.
So that's great.
Wait, almost.
Okay, I got my hair protection on. You got your hair protection on?
What's that?
Hello? Oh, hi, Mom. No, I'm shooting the show right now. I can't. Science.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large.
Science Max!
This episode of Science Max is all about storing energy and releasing it.
Yeah. Let's try it out for real.
Storing it in a giant spool racer. Plus a domino chain reaction, mousetrap chain reaction, popsicle stick chain reaction, and more. All on this episode of Science Max Experiments at Large.
Okay, 3, 2, 1, go.
Greetings, Science Maximites. Welcome to Science Max Experiments at Large. Wow, I really need some more energy. Fortunately, I have some saved up. Ah, that's better. Yeah, I know what you're thinking. Storing energy like that doesn't make a whole lot of sense, but you can store energy, and that's what this episode of Science Max Experiments at Large is all about. In fact, I'm gonna store some energy in this container simply by putting it up here on the top shelf. More on that later. But right now, let's look at another way that you can store energy and release it in a really fun way. We're gonna make a spool racer, and it's pretty simple. Here's all you need. You need some science ribbon. Now, if you don't have science ribbon, you can use regular ribbon, but the ribbon really isn't important. It's the spool that's important.
You'll also need a washer, elastics, pencil or pencil crayon, popsicle or craft stick, and science tape.
Science tape is the same as invisible tape, except I use this one only for science. Here's how you build it.
Break the popsicle stick so it's smaller than the diameter of the spool. Then put the elastics on top of the pencil and pull them tight
thread the popsicle stick through, and feed it all through the hole of the spool. Grab the elastics on the other side and pull out the pencil, and everything will be threaded perfectly. Then stick on the washer and thread the pencil through. Finally, tape the popsicle stick down so it doesn't move.
And if any of these steps are a little too fast, don't worry. All of the instructions are up on the website. That was cool. I can't make it go away. I can only make it come up. So there you go, a spool racer. And here's how it works. You spin the pencil around, and that twists the elastic. Now that elastic is gonna wanna unwind, right? So just keep spinning that pencil around until it's good and tight. And then when you put it on the ground, the pencil's gonna wanna unwind, but it can't because the table's in the way now, which means that the energy is gonna transfer to the spool, which is gonna turn, whoa, and it's gonna drive away. Yeah, let's try it out for real.
So why does this work? It works because the elastic is coiled, right? Yes, and because I'm putting in the energy to twist it. You see, I'm putting in effort to spin this pencil crayon around, and then when I've finished, all of my effort has been stored in the elastic. When I let it go, my energy transfers
Into movement. So that's, that's what we're gonna do today, Science Maximites. We're gonna max out the spool racer. I think Anthony would really know how to help me with this. So, I'm off to the Ontario Science Center. Come on. What happened?
You okay?
Anthony.
Yeah, hi.
Oh, were you in the middle of something?
Don't worry about it, yeah.
Oh, okay. Sorry about that. You know what, I was wondering if I could get your help with something.
Sure, yeah.
Yeah, one word. Spool racer. Actually, that's two words. Spool racer. Yeah, you want to help me max out a giant spool racer?
Yeah.
Awesome, let's go back to Science Matt's headquarters. Okay, Anthony, today I want to max out the spool racer.
Awesome.
Right, so you twist up the elastic and it goes from potential energy, all stored, to kinetic energy. Whoa, there we go.
That's awesome.
So, not too hard to design. Should be fairly easy to max out.
Yeah, really simple couple of parts here. We just got elastic band inside.
Yep.
And then this big long pencil to store the energy and then release it.
And the most important part
is spool.
Is the spool.
Exactly.
And I know where we should start.
Where's that?
Right here. This is an industrial cable spool. So the big, thick electrical cables, they come wound on this thing.
Yeah, okay.
So I figure we start with this.
Got it.
And the good news is that it's got a hole already. And check it out, it rolls really well, right? Okay, cool.
Okay.
So, bungee cord?
Yep.
And long pole or something?
Yep.
And we're ready to go.
I guess let's get some parts.
Okay.
Okay.
Oh, hey, how you doing? You want to buy something? I got a lot of stuff here, and I got a special today only. Potential energy, huh? I will throw in some potential energy with any order. You see this stuff on the shelves here? The stuff on the higher shelves has more potential energy than the stuff on the lower shelves. Don't believe me? Here, hold on. Look at this state-of-the-art traffic controller. Right now, it's sitting up here on this high shelf. Now, if it were to fall, it would be going fast, which means it would have a lot of kinetic energy. You see, when it fell down, it had enough kinetic energy to completely break itself apart. Yeah, well, that's the difference between potential energy and kinetic energy. Look at this bagel, just sitting here, not moving, minding its own business on top of this ramp. It's all potential energy and no kinetic energy. And when it gets to the floor, it's all kinetic energy and no potential energy. Woohoo! And now it has neither because it's on the floor and it's not moving. 5-second rule. And now you know your energy. So what do you say? You want this thing? Tell you what, I'll give you a discount because you know, it's gently used. Hey, I'll even throw in this bagel, huh? Also, gently used.
Anthony and I are maxing out the spool racer. We start with a long coil of bungee cord, which is kind of like a giant elastic, and feed it through the spool. Then we put on a big piece of plastic to act as our washer and use a long pole as the pencil. We flip the spool on its side to wind it up. Then we flip it back and it's ready to go.
All right, so we have it all wound up and we're ready to try it again, but with one change.
Phil,
Yeah,
what's with the trike?
I ride the trike.
It's like I always say, what's the point of building something big if I can't ride it?
There's no way you're gonna fit on this thing.
No, I don't put my feet on the pedals. I put my feet here on the back, right? And then-
Okay, yeah, I get it. You got it?
Hold on, I gotta do my helmet up.
Safety first. You ready?
I'm on it.
Okay, 3, 2, 1, go.
Oh, it's working.
It's working. Amazing.
All the stored energy in the bungee cord is being released and the spool starts to turn. There's even enough energy that I can get pulled along behind it.
It's not going that fast, though.
No, and
It's pretty good, though. It still pulls me. Right?
Yeah, pretty good.
So, spool racer, actually able to get pulled by it.
Yeah.
You know what? I think we can go even bigger.
Bigger.
Yes.
Well, what did you have in mind?
I'm glad you asked. Yeah!
What is this?
This is an industrial cable spool, and this is the biggest size that they make. And I thought we would do the same thing with this. What do you think?
I think this could generate a huge amount of energy.
Okay, so all we gotta do is just build it just like we built that other one.
Just bigger.
Except way bigger. Let's do it. When you set a domino on its end, you're giving it potential energy because it can fall. Ooh, and when you put two dominoes together, you can start a chain reaction because that one will fall into that one. But it's a lot more fun with more dominoes.
Setting up a run of dominoes is a lot of fun, but it takes a flat surface and a steady hand. And if you want to do it yourself, add gaps, so if one part falls, it doesn't take out the whole run.
Last one. There. I had some dominoes left, but I did it. I made the Science Max logo. See?
Science
right?
Max!
Sort of. Let's see how it works. Ready? Yeah! Now it's time to max it out. Giant maxed out dominoes! Woohoo! Even though these dominoes are giant, they're still gonna work the same. They're standing up on their ends, which means they've got some potential energy. And when I give this one a push, that potential is gonna turn into kinetic energy, and it's gonna knock the next one, and the next one, and the next one. I hope. I don't know what's gonna happen, but let's find out. You ready? Okay, 3, 2, 1. Giant dominoes! Yeah, science! The problem is, when you use dominoes this big, setting them up again is a real chore. This is a mousetrap, but don't worry, no mice are gonna be harmed in the making of this episode. Mousetraps are a great example of stored energy. You see, in order to set a mousetrap, you have to push this bar back, and it's hard to do because the spring holds it. And then you set the mousetrap by putting this little lever underneath this very sensitive trigger, and once you have it set, all that energy is stored as potential energy, but it'll go off with just the slightest touch, releasing the energy. So what if I had a number of mousetraps and they're all set and all of that potential energy is stored up, and I dropped a number of ping pong balls on them? Well, then I could set off a chain reaction where one mousetrap flies and hits another mousetrap that hits a ping pong ball, and then they all go. Now, this is something you can try at home, but do not set the mousetraps yourself. it can really hurt if it snaps on your fingers, so you should probably ask an adult to help you, and then you can see how brave the adults in your house are. Okay, you ready? Here we go. Mousetrap chain reaction. And last one. There we go. And now, let's max this out.
Let's do it with 90 mousetraps.
And this is a crate of ping pong balls. So, let's see what happens when we put them together. There you go. Maxed out ping pong ball mousetrap chain reaction. Awesome.
Ready?
I'm on it.
Anthony and I have built a large spool racer.
Oh, it's working.
It's working.
And it worked so well, the only option was to go bigger.
This is an industrial cable spool, and this is the biggest size that they make.
I think this could generate a huge amount of energy.
Building our giant spool racer is the same process as the other builds.
So the steps are exactly the same, but on a larger scale. And this time, we're gonna use, obviously, the large spool, and we're gonna use this 2x4 as our pencil windy thing.
Coil some bungee cord, feed it through.
Ready?
Yep.
Okay, here it comes.
There we go.
Got it?
Haha, yeah.
Add a washer and a long 2x4 to act as our pencil.
And now we stick the giant 2x4 inside the coil.
Just about. Yeah, we got it.
There we
cool.
go.
And we're ready to try it out.
So it looks like we're ready to go.
Yeah, exactly.
Do you want to do it in here or you want to do it outside?
Oh, definitely outside.
Okay, let's go.
Yeah, okay, cool.
Yep. Oh, it's heavy. Batteries are great at storing energy. They store electricity. Batteries. But if you're like me and you have a whole bunch of batteries and you don't remember which are the good ones and which are the dead ones, there's a trick that you can use to find out. Get a frying pan or a brick or concrete floor or something else that's very, very hard and an adult's permission. Here's the secret. Dead batteries will bounce and batteries that still have some life in them won't. Watch. Good battery. Dead battery. Now, it's a little hard to see, but listen. 1 hit, 2 hits. Here's what's going on. See, batteries store electricity in the form of a gel, sort of like modeling clay. This is modeling clay, fresh from the fields, where the pits, the mine, wherever modeling clay comes from. And this is modeling clay I've left out for about 5 days, so it's all dried up and hard. Now, when modeling clay is new, it's all wet and soft, and when you drop it, it doesn't bounce very well. I've left this piece of modeling clay out to dry for about 5 days. Now it's all dried up and old, and it bounces. New, old. So, same thing with the battery. Good batteries won't bounce, and bad batteries will. Science. Here's a fun chain reaction you can do with popsicle sticks, or craft sticks, because these ones are a little bit wider than popsicle sticks. It is because these kind of sticks are slightly bendy, and when you bend them and put them together in a pattern in a certain way, you can keep them under tension, and then they want to snap back, and then they'll fly. So here's how you make the pattern. Ready? You take a popsicle stick or a craft stick, and you put it down on the table. I know, okay, it's a slow start. And we take another one and put it across. Now comes the secret. The secret is over and then under. You want to put it over one and then under another, like that. And then this one, over, under. Put it over the one that looks like it's the top stick and under the stick that looks like it's the bottom stick. And then it starts to hold tension. It starts to hold the potential energy.
Continue this pattern. Each stick goes over and under the 2 sticks at the end.
Now here's the trick. Soon as this one lets go, then that one will let go, then that one, then that one, then that one, and that's how you get the chain reaction. They all start flying up. So you have to build it with never letting go of that last stick. You gotta always remember to keep a hand on it, or else you'll have to start again. So, okay, so you ready? You wanna see me let it go? Here we go. I know, that isn't so great because it's better if it's a longer chain. So fortunately, I have a longer chain. I've got a binder clip on this end, keeping the craft sticks together. Ready? 3, 2, 1. Wow! Release of kinetic energy from the potential energy of winding all the craft sticks together. Fun, and you can totally do it at home. Now, let's max it out. Behold, almost 800 craft sticks in a long, nicely designed triangle. Ready? 2, 1. Yeah! Craft stick chain reaction. I'm gonna go get something to clean this all up with.
All right. Anthony and I have built a giant spool racer and have taken it outside to try it out. In order to wind it up, we flipped over the last version on its side. But this spool weighs 200 kilograms. Easy to roll, almost impossible to flip over.
Come on, get it.
I don't think it's gonna work. It's too heavy to move.
Yeah.
We should have thought of that before.
Well, I'm sure we'll think of something.
So Anthony and I thought about it. And thought about it. And thought about it.
I got it!
What?
No.
But you...
And the answer finally dawned.
What if we roll it this way? Because then that would wind it up, right?
That's brilliant!
By rolling it backwards, we wind up the bungee cord in one direction, which will make it want to unwind in the other direction. Anthony and I roll it across the parking lot to get it wound up tight.
I don't think I can hold it anymore.
Okay. Let go. Okay, it's wedged.
It worked.
All right, one more thing. We're gonna hook the trike up to this one as well.
Okay.
So right now, it's all wound up, and when it gets moving, the potential energy in the coil will turn into kinetic energy. Now, just in case you're tempted to try this at home, I need to tell you, do not try this at home. We're trained professionals, right?
Yes.
Yes. Well, as much as anybody can be trained for this, because no one really does this.
Are you ready?
Ready?
Okay, here we go.
Whoa. It's working!
It's working!
Yeah!
Sure enough, all the potential energy we stored in the bungee cords starts to unwind, which rolls the spool and pulls me along behind it. What's more, that big heavy spool has a lot of momentum. So when it gets going fast, it just wants to keep moving. It wasn't long before I had to jump off.
That was amazing!
All right, that had a lot of kinetic energy.
That was a ton of kinetic energy.
There you go, Science Max, experiments at large, massive spool racer. Your turn next?
Yeah!
Okay. So that's what we're gonna do today, Science Maximites. Whoa! We are going to learn how to juggle. I can't hear you, I've got dominoes in my ears. And you put it in, and whoa, and now it's all broken. Well, here's a trick. Here's the trick. It's me disappearing. You see? When it would, blooper reel? Blooper reel.
Okay, hi.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! On this episode of Science Max, I'm on a quest to harness the power of lightning. Its balloon-sticking, hoop-levitating, hair-raising power is all thanks to static electricity. Hold on to your grounding rods. There's electricity in the air. All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Welcome to Science Max, Experiments at Large. My name is Phil, and today on Science Max, we're going to be harnessing the awesome power of lightning. How are we harnessing the power of lightning, you ask? With this balloon. I know what you're thinking. You're thinking, Phil, what's similar between a balloon and lightning? Well, nothing right now. But behold, as I use the power of static electricity and rub the balloon on my head. Because basically that's how it starts. You see, when I rub this balloon on my head, it's stealing electrons from me, creating a positive charge in my hair and a negative charge in the balloon. And the interesting thing is, you know that things with opposite charges attract each other, right? Something that has a positive charge will attract negative things and vice versa. But anything with a charge will attract anything with a neutral charge. See all these things on the table? They all have a neutral charge, which means they've got equal amounts of positive and negative. Right now, this balloon is building up a big negative charge, which means it will be attracted to all of these things. This can of Science Max soda, it has a neutral charge. The balloon has a negative charge, which means the can will be attracted to the balloon. And this paper is neutrally charged, which means the paper will be attracted to the balloon. And if you hold the negatively charged balloon next to neutrally charged sugar, haha, sugar storm! And you probably, wait, I don't want to get sugar in my hair. And you probably know this trick. If you rub a balloon on your head, you can stick it on the wall. Ha-ha! But what does any of this have to do with lightning? Well, the same thing is going on with a lightning bolt. The clouds become negatively charged, and that negative charge wants to equalize itself with the ground, which is neutrally charged. And that lightning bolt is the electricity jumping from one place to another. And you can see this yourself if you rub a balloon on your head and you put it next to something metal like a doorknob. There'll be a spark. But here's another thing you can do if you don't have a balloon, which I guess I don't anymore. Rub your feet, if you're wearing socks, on a carpet, and then turn out all the lights and touch a doorknob. You might be able to see a spark jump from your finger to the door. That's lightning in a very, very small form. So that's what we want to do today on Science Max Experiments at Large. Max out lightning! I think I'm going to go to the Ontario Science Centre and ask Heather her advice. She really knows her stuff. I'm going to go see if she's busy right now. Come on.
You got the portal fixed, though.
Well, it's not exactly fixed. It's still got a couple bugs that I'm ironing out, but I stopped coming in 10 feet above the floor.
Hey.
So that's a step in the right direction. Anyway, Heather, I've come here because I want to ask your advice on something.
Yeah, for sure.
Awesome. So what I am doing is creating lightning. So this is where I'm at right now. So this is a balloon. I blow up the balloon, and then I rub it on my head, and it creates a static charge, right?
Yeah.
Just like in the lightning bolt between the clouds and the ground. So I was wondering if you could help me maybe max that out, and I thought the perfect place to start would be a larger balloon.
Ooh, right on. Actually, yeah, I like this.
Yeah.
I've got a big balloon, if you just give me a second.
Sure.
All right, catch.
Okay. All right, giant balloon. So what I figured is I'll just start rubbing it on my head.
Okay.
And then we could maybe stick it to the wall or something?
Yeah, I think instead of a wall, we can even try on this whiteboard here.
Oh, okay, great.
Keep rubbing.
I'm
You're doing great.
rubbing. Okay, ready?
Yeah.
Here we go. So that didn't exactly work.
Yeah.
Both of us rubbing our heads on the balloon.
Okay.
And go. Wow, that was a whole lot of nothing.
Well, we've got a really heavy balloon here.
And I feel like our heads are only this big, so we can't cover as much surface area of the balloon.
Fortunately, you can also build up a static charge by rubbing a balloon on a sweater. Or if your balloon is giant, rubbing sweaters on your balloon. But even that didn't work so well.
I think what we need to do is come up with a better way to create a difference of charge.
Yeah, let's forget about the balloon.
You have something else?
I have something else really awesome here at the Science Center. You want to check it out?
Yeah, absolutely.
Yeah, right.
Should we take the sweater and the balloons, or should we leave them here?
We'll leave them here.
Okay.
So here's how static electricity works. Normally, everything has equal numbers of positive and negative charges. That's when things are said to have a neutral charge. But when you rub a balloon on your head, the balloon develops more negative charge than positive because it pulls electrons from your hair. The same thing happens in clouds during a storm. The cloud develops a negative charge when water molecules start bumping into each other. A lightning bolt happens when the negative charge in the cloud gets so big, the attraction to the positive charge in the ground gets strong enough that the electrons can make the jump all the way from the cloud to the ground, and you get lightning. Heather and I tried to max out the static on a balloon, but a big heavy balloon just doesn't hold the same charge.
That didn't exactly work.
Yeah.
But we're only interested in maxing out the static charge, and Heather knows just what to use.
Wow. So this is the Ontario Science Center electricity show?
Yes.
Okay, so where's the electricity part?
The one we're going to be playing with is right there.
So the giant mushroom.
Yeah, well, it does look like a mushroom.
We're gonna make some sort of electricity salad.
All right, head on up onto that platform right there. And I need you to put one hand on that silver ball, yes. So the way it works...
Nothing is happening.
Patience.
Okay.
Once I turn it on, when I engage it, this is going to steal your negative charge. So it's going to steal your electrons. So if it steals electrons, you're going to be positively charged.
So it'll make me more positive.
Even more positive.
Yay! Woohoo! I am positive!
Here we go.
Woo!
This machine is called a Van de Graaff generator, and it pulls the negative charge away from the person touching it.
That is great!
Instead of having equal amounts of positive and negative charges, you become positively charged.
Woohoo! Science hair! Yeah!
Like when you try to put two positive ends of magnets next to each other, each hair on your head starts to repel the others and be repelled from your head.
Science hair! Dude!
So your hair stands up.
Yes! Woohoo! I can't see anything. So this is more of a machine to generate hair standing up, but it doesn't make lightning.
Oh, well, actually, I have a demonstration in my back pocket. This is going to help us to create lightning. This is our grounding rod.
It is my scepter of science.
And so we're going to use this to continuously provide that negative charge.
That's why it's plugged in.
That's why it's plugged into the ground, yeah.
Okay.
Okay, so then if you touch it to that metal ball, got it? Not too exciting, right? So pull away and let's see what happens.
Whoa! This is what I'm talking about.
Very good.
The Van de Graaff creates a positive charge. The rod has a neutral charge. When the difference becomes big enough, the charge jumps the gap.
Behold, I have the power of lightning! So it's the difference between the positive and the negative is what we want when we want to make a lightning bolt.
Yes.
So is there something we can use to make that happen? Large difference of charge?
Yeah, I think I have just the thing.
Oh, yeah?
Yeah, you want to check it out?
Absolutely.
All right,
Okay, let's go.
would like to move electricity from here to there. Well, what you need, my friend, is a conductor. All right, a little more arpeggio this time. No, not that kind of conductor. All aboard? No, not that kind of conductor either. This kind of conductor. I know what you're thinking. You're thinking, hey, that's just a piece of metal. Well, that's right. That's because you're smart. This is a circuit. Electricity flows from this battery along the wires and into the light bulb. But Sal, you cleverly observe, the light bulb is not lit. This is true. That is because we have a gap in the circuit. And air is not a good conductor of electricity. Is metal a good conductor of electricity? Let us find out. Wahaha! Metal is a good conductor of electricity. What about wood? Nope. What about this horseshoe? Is a good conductor. Will this sandwich conduct electricity? Nope. No. What about this plastic fish? Nope. What about this pickle? No, pickle is not a good conductor. That's why we make electrical wires out of copper and not pickles. You know, in case you were wondering. Lightning bolts make interesting patterns. That's because the electricity is searching for a way to get from one side to the other. But it's hard to see the patterns of lightning bolts because they happen so fast. Fortunately, using the power of science, we can observe these patterns for ourselves in a motion we can perceive. I'm going to use electricity to recreate a lightning bolt pattern. I've got 2 nails in a piece of wood here, and I'm going to attach electrical leads to both nails. Now, the electricity wants to go from that side to that side, but it can't. It has to go through the wood, and wood is not a very good conductor of electricity. Now, this is very dangerous. I need a special machine even to pull this off, so this is definitely not something you want to try at home. In fact, I'm gonna stand way back here when I turn it on.
Like water, electricity tries to find the easiest route to get from one place to another. But sometimes that involves branching out until the right connection is made. Lightning bolts do the same thing when they branch out between the clouds and the ground. Finally, there's a spot where the branches meet and the circuit completes itself. Then the electricity follows this one path, ignoring all the others.
And there you go. We just watched a lightning bolt happen in slow motion. Haha, science.
Back to our main experiment where Heather and I are on a quest to use static electricity to recreate a lightning bolt. Our experiments with the Van de Graaff generator had some hair-raising results, but Heather has another experiment she wants to show me.
This is Jacob's ladder.
Oh, so this is another way to make lightning.
Yes.
Lightning?
We're gonna see, yeah.
Let's do it.
All right.
How do we get it to go?
All right, so we want to turn it on.
Behold! Oh, turn it on,
Not-
okay.
not-
Go!
Oh.
Ooh, look at that!
You can actually see that light climbing up between the 2 copper wires.
That's why you call it Jacob's ladder, because it's got the rungs of the ladder.
Yeah. Between these 2 points, there's a really great charge difference, right?
Okay, so what's the difference?
10,000 volts if you're looking at it.
10,000 volts.
Yeah.
And volts is how you measure the difference in charge.
Exactly.
Why does it go up?
So it goes up because rather than just staying at the closest point, is because we're heating up the air.
Oh,
point,
so
yeah.
hot air rises.
Hot air rises.
And it takes the electricity with it? So if we cooled the air, it wouldn't go up?
Wouldn't immediately go up, yeah.
And there it goes, and it heats back up again.
Yeah.
That's neat. Okay, so we have a Van de Graaff generator. We got a Jacob's ladder. Are there any other devices that make lightning like this?
Ooh, yeah, there's other things like the Tesla coil, really high.
I have a Tesla coil.
You have a Tesla coil?
I do. I've got one at the lab. I've just never known how to hook it up.
Oh, I can help with that. Yeah.
Really?
Yeah.
Okay, let's do it. Let's go back to the lab.
All right. Well, yeah.
I'll turn that off. Okay.
Yeah, safety first.
Okay.
By now, you're probably an expert on what happens when you rub a balloon on your head, right? The balloon becomes negatively charged, which means it will attract anything of an opposite charge, or anything positive, or anything that is neutrally charged, like, well, like me. Look at the hairs on my arm when I bring the balloon close. Whoa! You see, the neutral charge in my body is being attracted to the negative charge in the balloon. So if something is negatively charged, what happens if you bring something else negatively charged nearby? Well, they'll repel each other. And here's an experiment you can do to make something fly using static electricity.
You'll need a balloon, a sweater, scissors, and a plastic bag out of the thinnest plastic you can find. Fold the bag up and cut off the bottom. You don't want that part. Then cut another strip from the bag. This will give you a hoop of plastic. I find it works better if you break it and tie it again. Lie it flat and rub it with the sweater. This will give it a negative charge. You'll know you've got enough of a charge when it really wants to stick to the table.
Then take your balloon and rub the sweater on the balloon to charge it up.
Because both the balloon and the hoop have negative charges, they repel each other.
Then put them together and it will repel.
And you can get the hoop to levitate.
Ha-ha, a floating bag of static charge. But here's the thing, you need to keep it away from your body, because if you get close, the bag will stick to you, because you're neutrally charged and the bag is negatively charged. Pretty cool, right? Well, let's max it out. Maxed out floating static ring. Whoa, no. Yeah! Look out, look out! Oh, no! Oh, sorry about that. Oh well. It was fun while it lasted. I gotta charge these up again.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. I didn't see you there. My name is Buster Beaker, and welcome to Cooking with Science. Let's say, for example, I've spilled the salt. Oh no, look at me. I've spilled the salt. Oh, there's salt all over the place. Not really a big deal, right? All you have to do is clean up the salt, put it back in the container. But oh no, I've also spilled pepper on the salt. But that's all right. You might be able to carefully separate the But no! Oh dear, look, the pepper and the salt are all mixed together. What do? Well, here's how you can save the day using the power of science. All you need is a cloth and a plastic spoon. Like this one here. Just rub the plastic spoon on a cloth, and you'll be charging it up with a negative charge of static electricity. If it's got a negative charge, it will attract anything that has a neutral charge, just like the salt and pepper. But I know what you're thinking. How will we separate them? Well, here's the answer, my friends. Pepper is lighter than salt. Observe. So if you hold the spoon high enough, the pepper will be attracted and make the jump up to the bottom of the spoon, but not the salt, as long as you've got it high enough up. Because the salt is heavier, you'd have to bring the spoon closer, which we're not going to do. And if you tap it off to the side, you'll make a nice little pile of pepper, and there you go, separating pepper from salt using the power of science. Thanks for watching Cooking with Science. I'm Buster Beaker.
Heather and I have been on a quest to recreate lightning using static electricity. We've gone from balloons to a bandograph to a Jacob's ladder, each more lightning-y than the last. Finally, Heather suggests we use a
Tesla coil.
Oh, is this named after Nikola Tesla?
Yeah, he invented it.
Oh, one of the founding fathers of electricity, right? I love Nikola Tesla. He's cool. So how does it work?
So the way this works is it is a step-up transformer, meaning we take a lower voltage and bring it up and ramp it up to a much higher voltage.
Okay, so normal voltage is 120 volts. That's what we have a normal plug-in socket.
Typically, we're getting it out of, yeah, exactly. And we're gonna ramp that up to really high amounts, upwards of 25,000, maybe even 250,000.
Wow.
Volts.
That's a lot.
And all that charge buildup we're gonna see something pretty amazing happen.
Okay.
Do you wanna see it?
Yes, we stand back there, right?
Let's check it out. And
The Tesla coil builds up a charge which jumps through the air to this neutral rod, just like a lightning bolt.
We made a lightning bolt! That totally jumped a long way. That was impressive.
that was a really good one.
So can you control it?
Yeah.
Okay, show me.
You wanna see? All right. I'm going to lower my frequency.
Okay.
Let's see what happens.
Oh, that's amazing. Oh, it's like a scattered lightning bolt. Oh, wait a minute. So you can play different notes?
Play different notes.
I need 5 minutes. Hold on.
Okay.
Okay. All I need is 5 minutes. You know, I was thinking is if you can make different, hold that for a second. If you can make different frequencies, that means you can make different notes, right?
Right.
So I don't need that either. Hold on. Ah, that's not what I need. Okay, one more thing. Can I get that hammer? Okay. Yeah. Okay, ready to go.
So what is this?
When you told me the Tesla coil could play different frequencies, I thought we could make different notes come out of the Tesla coil, so I programmed it to play the notes of the Science Max theme song.
What?
Yeah! You wanna hear?
Yeah.
Let's try it. Yeah! Science Max, experiments at large, lightning bolts!
Creating lightning!
We have created lightning! Woohoo! Lightning dance! No. I give up.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today's episode is about friction.
How can I hang on to this rope without falling?
Can we reduce it so we can slide around?
I'm going towards the wall!
Can we increase it so I can climb a wall?
Ha ha! I did it!
Can I use it to fly? Yup! Friction, today on Science Max Experiments at Large.
Hey, Science Maximites, slippery. But that's okay, because today we're talking about friction. Friction is a force that is everywhere and happens when any one thing rubs against any other thing. We do lots of things to increase friction, like wear shoes with big treads on them. And we can do things to reduce friction, like the experiment we're doing today. We're gonna build a hover disc, and it's very easy. You take some cardboard and cut it into a circle, just like this. Then put a hole in the middle of the circle. You might want an adult to help you with that. And then take a plastic drink bottle cap, like this. I like use the ones that you get on sport bottles because they have a little nozzle that pops open or closed. And then you glue it around the circle and you get this. Then you need a balloon. So you blow up your balloon. I know you know that step. And then twist the balloon so it doesn't get away from you. When it's nice and twisted, you can stick it over the drink bottle cap like this, and then untwist it. And this is why I like to use the plastic drink bottle caps that come from sport bottles, because you can open it when you want. And when you do, your disc rides on a cushion of air, reducing the friction with the table, and it's almost like it's sliding on ice. You can also use CDs if you want to do a different design. Just make sure you're using CDs you never want to listen to again. Now, if any of this is too fast, don't worry. You can always go to the Science Max website, where we have all of the instructions. And now, it's time to max it out. We're gonna see if we can make a human-sized, rideable, low-friction hover disc. I'm going to the Ontario Science Centre, where hopefully I have an expert that can help me. Door is stuck. I think there's a little bit too much friction with it. Okay. That's got it.
Oh no, this isn't the Science Center. Did I go back in time again?
Oh. It is the Science Center. Helena, hi.
Hey, Phil. You're here to see the hover disc.
Yes, please.
All right, come on, right this way.
So I made one in the lab that works pretty great. It's on cardboard and it has a balloon. The one you have here works on the same principle?
Yeah, it does. But you know what? My friend Russell has some ideas about making something like this, but even bigger.
Do you think we can make one big enough to ride?
Maybe, yeah.
All right, well, let's take a look at the one you have here. Oh, I see. Right, this one works the same as the one I made. It's really hard to move the disc, but if you add some air, it floats like a dream.
There we go.
Great, so let's ride it.
Whoa, Phil, not this one, the one upstairs. You can ride that one.
Oh, okay.
Yeah.
Should we bring this one just in case?
No, it's a little heavy. I think we can leave it there.
What if we need it for reference?
No, I'm sure we'll be okay.
It is pretty heavy.
Yeah,
but...
come on. Let's go. Russell's made it.
Are you sure we won't need it?
I'm positive.
Okay, but if we have to come back, I get to say I told you so.
Okay.
All right.
Hey, Ramona, you change your hair? Yeah, it's nice. It's like doing this now. Because but now it's, yeah, I like it. You should give me the name of your guy, because I wanted to, hey, oh, hey, how are you? You ever think to yourself, no matter what I do, I can't seem to get anywhere. I can't get enough traction? Well, you, my friend, need some more friction. Which one of these two shoes has more friction? Take a closer look. Huh? Right, bam. This one doesn't have a lot of treads. It doesn't have a lot of friction. But this one, it's got metal spikes on the bottom. This is called a cleat, and the spikes are for helping you grip onto the grass when you're playing soccer or golf, increasing its friction. Why do you think skis are smooth on the bottom? Come on, look at that. It's so smooth and glidey. My hand I can barely even touch the surface. It just slides right off. It's sort of glidey and smooth. They're smooth to help you glide across the snow, reducing their friction. Why doesn't this box slide down this ramp? Friction. This roller skate has wheels. Wheels reduce friction. But when I push the roller skate, how come it doesn't just keep rolling forever and ever and ever and ever? And going all the way around the world and writing a memoir. Say it with me. Friction. Louder. Friction. Can't hear you. Friction. A little too loud. Friction. Ease it back. Friction. How can I hang onto this rope without falling? Friction. How can I jump down on the floor without falling over? Friction. And now you know your friction. Your friction. Your friction. Come on. Uh-oh. Oh, Ramona, the friction sign is broken. Reset.
Uh-oh. The plan is to take our small hover disc and make one big enough to ride. So I'm off with Helena to another part of the Science Center to meet Russell, who has some ideas on how we can do it.
Oh, hey, Russell.
Hey, hi, Helena. Hey, Phil.
How you doing, Russell?
How you doing, Phil?
So this is the hover disc.
This is our small hover disc, yes.
How does it work?
Well, obviously you sit on here,
right.
Air will go into here. It gets vented through all these separate holes here, so we get an airflow over the entire area. Hopefully this will work to pick someone up. All we need is...
air.
Oh, well, that's easy, because the small one worked like this, so we just put the balloon on, right?
I hope you got that.
Okay, so we put the balloon on the... hold on. Larger balloon!
Okay.
Sorry.
That's okay.
Okay. Yeah. Uh-oh, twist it so it doesn't...
He's losing his air. All right. On you get. You grab
Right.
one side, I'll grab the other.
Okay, here we go.
Go.
It's not, it doesn't...
Feel way too much
It doesn't
friction
feel
on
like
it.
there's it still feels pretty frictiony. I think we might need something more than a balloon. So what do we do?
Well, I think we need more consistent air going through here.
Okay. So not a balloon.
Not a balloon. Something, I don't know, opposite to a vacuum cleaner?
Opposite to a vacuum cleaner. That would be
Like a leaf blower.
Like a leaf blower.
a leaf blower.
Right?
High five.
Yeah.
Awesome idea.
Yeah, leaf
so
blower it is.
why don't we make a couple larger discs when we'll hook some leaf blowers to them and we'll see what happens.
Definitely give it a go.
Okay, great. Carbon is an atom and is the basic building block of all life as we know it. You, me, all plants, all animals are carbon-based life forms. Other things are made of carbon too. Diamonds are carbon, coal is carbon, even pencil lead isn't lead, it's graphite, which is carbon. If you were to take all the carbon atoms in your body, you could fill 9,000 pencils. Of course, kind of prefer my carbon where it is. Our low-friction hover disc still had way too much friction. One of the problems that Russell mentioned is that the balloon just wasn't giving enough air. But then Helena had the idea of using a leaf blower instead. The plan now is to make a leaf blower powered disc by starting with a big circle of wood, cutting a hole in the wood where the air will come through, and then covering the bottom with a tarp that has many holes cut out of it for the air to escape. Because leaf blowers are made to push lots of air, hopefully there'll be enough for me to ride it.
Well, this is the business. Look at
That's
this.
amazing.
It's good, right?
Oh, yeah, I love the
So-
tube and that high volume of air through that.
Yeah.
So yeah, I think it's a dryer vent I just found it in the lab. And then this, of course, is a leaf blower. So I get on here, and then Helena, if you want to turn it on.
Yeah.
So once we fire it up, the air coming out from the bottom of the disc raises me up, and I float on a cushion of air. I can't control it! Because the friction between the disc and the floor is so low, I end up floating wherever Helena and Russell push me. I'm going towards the wall! It's like human air hockey! Okay. It's unstable. Do you want to turn it off? Wow, that worked amazing.
Not too much control, though.
I have no control whatsoever.
Yeah, no.
But this is great. So so we have the no friction down pat. I feel we need some way to actually move.
Well, something to push you along. I was thinking as you were going, like, you need like a broom or something.
A broom. Okay, yeah. What if we do like something low friction, like a broom, and something high friction, like that we could really sort of stick on the ground?
Yeah.
Yeah.
works for me.
And then we could build two of them, and we would have two discs and two ways of moving them.
Are we gonna race?
And we can race! Yeah! Okay,
Yeah.
great. That's what we're gonna do. Here is an experiment you can do at home with friction. This is a toy boat. Yes, you guessed that right. And this is a wooden plank. Correct, that's 2 for 2. I put the boat on the ramp and watch what happens. Nothing! The reason why is because the friction between the boat and the ramp is enough to counteract the force of gravity trying to pull it down. But watch what happens if I raise the ramp to the right height, the boat slides down because the friction isn't enough and gravity pulls it down. But when we change surfaces to this carpet, let's see what happens. Same angle, I can raise it higher, 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 because there's more friction between the carpet and the boat than there was between the wood and the boat. Now, if you're thinking that we're just gonna do it with a small ramp, you're wrong. Because of course we're gonna max it out. Hey, Helena.
Hey.
This is amazing.
Thanks, I made it myself.
Wow.
Ready to climb it?
Absolutely. Here we go.
Way to go.
Huh? No problem. So that was very easy.
Well, that's probably because the friction from your shoes is high enough so you don't slip.
Right, and the friction from my clothes is much lower, which is why I could slide down.
Right.
So how do we make it more difficult?
We probably have to make it higher.
All right, let's make it higher.
With the ramp at a steeper angle, I'll need more friction to climb up.
All right,
Ready?
I'm totally ready. Here I go. You try.
Okay, hold my drink. Here we go.
Oh, so clearly we are not getting enough friction between our shoes and the ramp at this angle.
We should add some carpet, because carpet would add some more friction between our shoes and the ramp.
All right, let's add carpet. Sorry, here's your drill.
Thanks.
All right, carpet.
Yeah?
Same angle.
Yes.
And why have we done this?
More friction.
More friction. Let's give it a try.
Hey, way to go.
Totally able to climb the ramp. So, what do we do now to make it harder?
Make it higher.
Make it higher. Wow, it's really steep.
I don't think you're gonna make it.
Sure, if I take a really good run at it, I think I can do it.
I don't think so.
Well, there's one way to find out. No.
No.
Okay, so I can't do it. Is that it?
Well, how about Velcro?
Wow.
Right? It'll give you more friction, so you can try climbing with this. We'll give you Velcro knee pads, Velcro shoes.
Velcro. Velcro handholds, Velcro knee pad, Velcro on my shoes, helmet for safety, Velcro fill, Velcro dance. Okay, you ready?
Ready.
All right, here we go. Ha-ha, I did it! Creating friction between me and this ramp means I can stay up here for as long as I... No. No, Velcro. No. No.
Phil, you okay?
Velcro! Friction! Your turn.
No.
Our hover disc worked well. So well that we decided to build another. If we have two hover discs, then we can race them using different kinds of friction to push them along. Something that has low friction, like a dust mop, and something that has higher friction, like a pole with rubber balls at the end. Rubber has great friction. That's why we make car tires and the treads of our shoes out of rubber.
Okay, we have a giant race course that we've set up. We've got two low friction hover discs, and I'm gonna use the low friction dust mop version to propel my hover disc. And Helena, what do you have?
I have the high friction rubber ball stick.
Start your engines! On your marks, get set, and go!
And we're off. Remember, Helena and I are using very different methods to get our hover discs moving. I'm using a low-friction dust mop, and Helena is using high-friction rubber balls. As you can see, my low-friction dust mop doesn't make enough friction with the ground for me to push myself. Helena, on the other hand, is having no problems.
Let's go! Let's go! Let's go! Let's go! Go ahead! You can beat him! He's way back! Oh! Bit further! Bit further! He's way back for the win! It's Helena!
Jay crosses the
Yes!
And there we have our winner. Yes! Over the finish line. It feels way back over there.
Oh, man.
I'm still stuck at the second turn. Way to go, Helena.
Thank
Nice.
you.
So what was the strategy? How did it work?
Well, pretty much while I was using those red balls, I was getting friction, helping me steer.
You know what? I think we need a little bit more thrust. That would work even better if we had something pushing us even harder.
Definitely.
Wait. I have an idea. Wait, hold. I need your help. Come on.
Okay.
I'm at iFly Toronto indoor skydiving to talk to you about friction. That's Mike. He's gonna help me out. Okay, here we go.
Phil is saying because there's too much wind. It looks like he's trying to tell us something about the friction. Yes, he's saying the friction from the air rushing up in the chamber is enough to counteract the force of gravity, which is why he's able to float or swim or whatever he's doing. Now it looks like he might be saying even something like air can have a lot of friction if it's going fast enough. And the air in this chamber is going fast, which is why we can't hear a word he's saying. Oh, well, he seems to be having fun. So how important is friction? Well, let's say I'm out for a drive. Car tires need friction to grip onto the road. Without it, my car wouldn't be able to turn at all. But that's nothing. Without friction, the bolts holding the wheels on the car wouldn't work. In fact, none of the bolts, screws, or glue on the car would work, and nothing would stop moving or stick to anything else. Even the trees would blow away with the slightest breeze. Friction is everywhere, and without it, nothing would work.
Okay, hover disc race round 2. This time we decided to have a little bit more thrust, so Helen and I are going to be using fire extinguishers. Now, do not use fire extinguishers at home. Fire extinguishers have a very important purpose, and it's not for this, but we got these ones special. Are you ready, Helena?
Oh, yeah.
Oh, yeah. Okay, here we go. Russell?
So, racers, start your engines. And go!
Using fire extinguishers gives us a lot of thrust. But because the discs we're riding on don't have any friction, wherever we point ourselves, we just keep going in that direction, which makes steering very difficult. Cars grip onto the road and can go around corners thanks to the friction of their wheels. When you have no friction, it's kind of like moving on an ice rink.
Oh, no! I'm out! High five! Yeah, high five! Yeah! Okay, wait. Oh, I ran out of fire extinguisher at the end there, so I had to cheat a little bit. So 1 for you, 1 for me, and all of them for friction.
Or the lack of friction.
Or the lack of friction. Science Max, experiments at large. What do we do next? Larger fire extinguishers?
I think so.
Okay. See you next time. I know where we can get some, actually. We can go, if we go to the fire extinguisher store where we got these fire extinguishers, I think we can get like a rack of extinguishers.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Carbon is an atom that is the basic building block of all life as we know it. You, me,
I hit myself in the head with the friction sign. That's more of an impact, not friction, really. How can you destroy my life anymore? Set, huh? Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large.
Science Max!
This
This episode of Science Max is a messy one. We're looking at solids, liquids, and gases, and things in between, like cornstarch mud. Today on Science Max, experiments at large.
Behold the power of states of matter! Greetings, Science Maximites! I'm Phil McCordick. I think I overdid it with the fog machine. This is Science Max, experiments at large. Can you even see me? Let's go over here. Today we're talking about states of matter. Now there are three main states of matter. Solid, like this table, liquid, like the water in this beaker, and gas. Yes, thank you. And we're also gonna be looking at the things that kind of go in between. Things that are sometimes solid, sometimes liquid, like cornstarch mud, which is very easy to make. All you need is water and cornstarch, which you can get at the grocery store. Mix it up however much you want. Just remember, 2 parts cornstarch to 1 part water. Twice as much of this than you have of that. Very easy. Mix it up and you get cornstarch mud, which sort of seems like a liquid unless you hit it. And then it becomes solid. But if I pour it, it's a liquid. Even if I hold it in my hand and I hit it really fast, it turns into a ball, and it will stay in a ball as long as I keep hitting it or squeezing it. But as soon as I stop, it turns into a liquid again. Now we're gonna max this out. We'll go through the portal and learn more about solids, liquids, and gases. Yeah, right. That's why I'm going to the Center for Skills Development and Training. And, oh no, wait, that's the code for the fog machine. Wait, stop. Stop, it seems to be stuck. Oh, never mind. I'll fix it later. Right. Hey, Judy, how are you?
Hi, Phil, how are you?
Good. Judy is going for her PhD in chemistry, right?
Yes.
Fantastic, because that means you can explain cornstarch mud to me. Now, is this a solid or is it a liquid?
Well, it kind of has properties of both. It's called a non-Newtonian fluid, so that makes it a liquid.
A liquid? Well, I mean, it pours like a liquid, but when you hit it, it's a solid. So why does it turn solid when you hit it?
So when you're pouring it, the particles are still far apart, so they can't interact with each other, and so they stay a liquid. But when you're hitting it, you're jamming the particles together, and they line up to become a solid.
Now, does it still work the same way if we have a lot more of it?
It should.
Great, because I've got this 20-kilogram bag of cornstarch, and I have 34 more of them.
Wow, that's a lot. But I think you'll need a much bigger container.
Much bigger container, great. I got some wood over there. Why don't you go, and I'll follow you.
All right.
I'll follow you. I'm coming. Yeah, thanks, Ramona. And give me one of them fizzy drinks. Not too fizzy, just sort of medium fizzy. Thanks a lot. Hello, do you have trouble knowing what is a solid, liquid, or gas? Are you confused by Jell-O? I mean, which is it? Is it a solid or is it a liquid? Water is a liquid, but what about when it's ice? Well, you gotta know your states of matter. There are 3 main states of matter: solid, liquid, and gas. And there are 3 rules that you need to figure out which one of them is which. Does it flow? Does it fit the shape of its container? And can you squeeze it? Rule number 1, does it flow? Solid, liquid, gas. Here's a gas. Does it flow? Do the particles pour over each other and cascade down? Yeah, they do. Does a liquid flow? Yeah, it does. Does a solid? Nope. Rule number 2, what happens when you put it in a container? Does it take the shape of the container? Gases take the shape of the container. Liquids takes the shape of the container. Solids do not take the shape of their container.
know what you're thinking. You're thinking, I get the whole pouring and taking the shape of the container, but come on. Liquids and gases, they do both of those things. Well, it all comes down to rule number 3. Can you squeeze it? Now, solids, you can't really squeeze them. Liquids, you can't really squeeze them. Gases, ha-ha, bam, you can squeeze them. You see, gases compress. Liquids and solids, they don't really compress very well. The other difference between gases and liquids is gases will take the shape and the volume of the container they're put in. Liquids don't do that. So there you go. Solid, liquid, gas. And the rules. Does it flow? Does it take the shape of the container? And can you squeeze it? Now you know your states of matter. That'll be $6.50. Cash only.
So what is cornstarch mud and how does it work? Well, cornstarch mud is a non-Newtonian fluid, which means it behaves differently than you, or Newton, would expect. Here's cornstarch, and here's water. Cornstarch is made up of large, blocky molecules like this. Water is made up of much smaller, rounder molecules like this. When you put them together, it looks something like this. It all has to do with how the molecules slide past each other. When you put light pressure or slow pressure on the mud, the water molecules and cornstarch molecules have time to shift out of the way. But when you put a sudden pressure on it, the water molecules squirt out of the way, but the cornstarch molecules don't have enough time. So you get a section that's nearly all cornstarch, which acts as a solid. Cornstarch mud is a shear thickening fluid. Shear is talking about the force of things sliding around, in this case, the molecules. So when the shear force is strong, the fluid thickens. Shear thickening. So here's the plan. If Judy and I make enough cornstarch mud, could we run across it? Let's find out.
Yeah, I think mine is just the right consistency. How's yours, Judy?
I think I'm ready too. This is much harder than I thought.
Yeah, it's really hard to get it mixed at the very beginning, but mine is ready to go. Okay, here we go. First batch. You ready?
Yep.
Dump it in. Woo! Woo! I thought that would be more.
I thought so too.
It's really not filling this up very much, is it?
No.
Huh, that's a lot of cornstarch. This is great, but I think we're gonna have to go a little faster than this.
I think we need some sort of mixing device.
Yeah, I mean, we don't have to do this by hand. We can get some sort of machine to help us.
Yeah.
Right on, high five.
Oh.
We shouldn't high five when we have this stuff on our hands.
Nope.
Yeah, good call. This science is delicious. This is rock candy. It's basically crystallized sugar, and you make it by turning a solid into a liquid and then back to a solid again. Here's how you can make it at home. You need a container that you're not gonna need for a while, and some water, some sugar. You can use brown or white. I like to use brown. And an adult. Here's why you need an adult. You want to dissolve 3 cups of sugar into every cup of water. And you can't do that unless you heat the water. So get an adult, a saucepan, and heat the water up, pour the sugar in, and keep stirring until it's all dissolved. Then pour it in your container and let it cool down. Then you'll need a shish kebab skewer, which is something you can get at the grocery store. Cut it down to the right size so it fits nicely into your container. And then dunk it in your sugar and get some crystals coated around the stick. These are seed crystals, and they get the whole process started. And now you have to wait for these to dry, otherwise they'll just fall off the stick when you put it in the water. So I've got one here that has dried out. You'll also want something to keep it from falling in the top of the container, so I'm gonna use a clothespin. Put it in there and dunk it in the container like that. And now for the final step, if you want, you can add food coloring. I like to use red because it reminds me of science. And I'm gonna use the stick to actually stir that up a little bit. There we go. Now, the dissolved sugar crystals in the water will slowly grow on the crystals that are already attached to the stick, and it will eventually grow into a rock candy pop. But it takes about a week. No, I'm just kidding. I've already got one that's standing by. Here we go. This one has been growing for about 7 days. And there you go, rock candy. Delicious science. Now, how could we make this any better? I mean, it's crystallized sugar. It doesn't get any more maxed out than that, does it? Yeah, it does. Come on. This is a giant container of sugar water, and I've been brewing a massive rock candy crystal in it for a while, but it's sort of getting a little bit too big to fit out the top of the container, so you know what? I'm just gonna put that back in there and chalk that one up to science because, well, eating a rock candy crystal that big will definitely not be good for my teeth, so yeah.
So our big experiment is to take a whole lot of cornstarch and fill a trough to see if we can run on it. But mixing it by hand was going to take forever. So Judy and I got a drill with a mixing attachment on the end.
Whoa, sorry. All right, so Judy, I'm noticing a bit of a problem here.
What is it?
Well, if I mix at the top, everything's fine. But as soon as I get it a little bit deeper, and then it gets really tough, and the whole bucket starts to spin, and the drill stops.
Yeah, I think it's because the drill's trying to mix it too fast. When we're mixing it by hand, it's slow, and you can still let it stay a liquid, but now you're just making it a solid.
Right, because it's a sheer thickening fluid.
Exactly.
So if you hit it really quickly with something, like the blades of this spinning really quickly in the thing, it'll suddenly turn into a solid, and it'll be really hard to mix.
Yep.
So we go slow. Going slow. Going slow. Suddenly realizing that if we go slow, we'll be here forever.
Yep.
You know what I think we need? Whoa, sorry. You know what I think we need? We need a different way to mix this.
Yep.
We need a way to mix more of it, and we need a way that it doesn't hit it with blades that suddenly go through it really quickly.
Something that can mix on a large scale, but slowly.
I have just the thing. Come with me.
All right.
The interesting thing about bubbles is they're a gas surrounded by a liquid. So get some dish soap and some water, and then be Science Maximites and find things around the house that you can make bubbles out of. Just about anything that has holes will do. Or, or I like this one. I call it the loud bubble. Or now it's time to max it out. I'm here at the Ontario Science Centre, and this is Anthony. Hey, Anthony.
Hey, how's it going?
Good. So you are amazing at bubbles.
I am. I've been practicing for a while. Let's get started.
Okay.
You're gonna make an okie dokie sign like this. You're gonna dip it right into our bubble solution. Come on, get right in there, right in there. Make sure you get it all. Oh, that's a little too much.
Well,
That's
then I
good.
can make two.
And then you're gonna keep that okie dokie sign. You're gonna blow very gently.
Nice.
I brought these two giant sticks here, and I don't know if you noticed, but I've got a smoke machine here.
Right.
So we'll turn that on, and then if you press that green button there, you're gonna shoot some smoke, and we're gonna try to catch that smoke in a giant bubble. You ready? Okay, and I'm gonna try to... Oh, that was so close.
great.
Did you see that one? You give it a shot. Nice! Oh, check that out! That was amazing! That was huge. Try it again. Let's see if I can get the smoke machine. Here we go. Go for it, go for it. Push right towards. Oh, check that out! You did it! Look at that! Look at that! No! Smoke, and it bounces on the floor because the floor, it doesn't have any oils like our hands do. Isn't that amazing?
That was
oh my
great.
God, that was so cool.
That was great. You know what I think we should do?
What's that?
Giant bubble, tons of smoke.
Done.
Okay, here we go.
Let's do it. You ready?
Giant bubble, tons of smoke. Go.
Awesome! Oh my God! Look at that! Amazing! Look at that! That's crazy!
Maxed out bubble. Well, there you go. Giant smoke-filled bubbles.
Awesome!
Yeah.
Judy and I tried mixing the cornstarch mud using a drill with a mixer attachment. but it didn't work. We should have known better. Here's the mixer in our cornstarch mud. Usually, a mixer works by going really fast and mixing everything together. But remember that cornstarch mud is a shear thickening fluid. So, when the blades of the mixer tried to go fast through the cornstarch mud, it did what it always does, turn solid. The faster and harder you try to move it, the more solid it will become. This means the only way to mix it would be if we made the drill go very, very slow, which wouldn't speed things up at all. So with the drill another lost cause, Judy and I need the biggest thing around that could mix stuff up.
Come on back. Good. Little bit more. Perfect. A cement truck is a perfect thing to mix because all we have to do is get all the cornstarch up in here and it'll mix it, and it doesn't move it too fast. It goes nice and slow, so hopefully a shear thickening fluid will be fine. I'm gonna get Judy. She's driving the truck. Hey, Judy, that's perfect.
The only problem is we needed to get all of those bags of cornstarch into the hopper of the cement truck.
I didn't think it'd be this messy.
We needed to call the entire Science Max build team to help us out.
This is possibly the messiest thing I've ever done. Awesome! Woo! Hey, Judy, you wanna lift up any bags?
I'm okay, thanks.
That's okay. I'm having a lot of fun, so I can do them.
Cool.
Oh no! Oh no! Oh no! Yeah! I got most of it. All right, I think we're done. I think that's enough bags. Let's start the mixing! So, what do you think, Judy? Do you think it's gonna work?
I think so, because you're mixing at a very large volume, but at a very low speed.
Yep.
So throughout the process, it'll stay a liquid until we're ready to run across it.
That sounds exactly like the kind of science I like to see. You know what I really like is that every time I move, more cornstarch comes off. It's like I'm a human fog machine. This is liquid nitrogen. Nitrogen makes up most of the air we breathe, but if you get it really, really cold, it turns into a liquid. The fun thing is you can use it to make other things really, really cold too, like this banana. I have frozen this banana solid thanks to the liquid nitrogen, and normally a mushy banana would not be able to hammer in a nail, but whoa, because it's frozen, I can hammer this nail into this block of wood. So that got me wondering, if I can turn a banana into a hammer using liquid nitrogen, could I turn a pumpkin into a sledgehammer? Let's find out. Pumpkin sledgehammer, take one. No, I think the answer is no. You cannot turn a pumpkin into a sledgehammer with liquid nitrogen. All you can do is make a really, really big mess. I'm gonna have to clean this up, aren't I?
Now we have a cement truck to help us do the mixing for our cornstarch mud. After making a giant mess getting the cornstarch into the cement truck, it's time to see if it worked.
Hey, Phil, how's it going?
Yeah, it looks like it's mixing pretty well. I'm really glad we're not doing this by hand, because it'd take a really long time. We've almost got it at the right consistency, but it's taken some time. But it's getting a little dark out, Judy. I don't know, do you want to quit and go home?
No.
Of course not. That's not what we do in science. Oh, here we go. Yeah!
Awesome.
All right, let's see it. Let's see if it's... I like how it comes down in little steps. And look, it's working just like it should. I hit it, and it's solid, but you can see it's pouring like a liquid. Yeah, here comes a big wave.
Wow.
Here it comes. Oh! Wow!
And it's totally filling up.
Oh yeah, filling up really fast. I think we should stop pouring very soon.
Yep, we may not have a big enough trough. Yep.
Liking it.
It's good.
Yeah. I think it's time. It's not even done pouring, but I'm gonna try it. Okay, you ready? Whoa.
Oh, and you did it!
Whoa. You can't. You have to get back onto the sides before you stop moving.
Or else it becomes a liquid.
All right, it's your turn.
Okay.
Here.
Go.
Okay, ready?
Okay.
You gotta hit your feet really fast.
All right.
Here, go.
This actually works.
Because cornstarch mud is a sheer thickening fluid, it means it stays a liquid until you hit it suddenly, like with your hands, or in this case, our feet. And then it turns to a solid. So as long as Judy and I keep slapping our feet down with enough force, we can walk on top of it.
One more dance.
All right.
And
let's
tell you
do
what,
it.
we'll do one more dance.
All right, let's do that.
Okay, ready?
All right.
And go. All right.
All right.
There you go.
We've done it.
Solids, liquid, gases. Thanks very much for joining us on Science Max Experiments at Large. Woo! Hey, Judy, catch. I have to be careful because the banana will shatter if I'm not careful. I think it's stuck on the bottom. I call this one the loud bubble. Oh, well. I call this one the loud bubble. I don't think I can do it.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, Experiments at Large. Science Max! This episode of Science Max is all about earthquakes.
Exciting.
How do we build something that won't fall apart when shaken? Plus a lot of other ways to shake things or build things.
Science!
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. My name is Phil, and this is Science Max Experiments at Large. Today, we're going to be looking at earthquakes. Earthquakes! Huh. Today, we're going to be looking at how to build something. That was supposed to happen earlier. Today, we're going to be looking at how to build something that stands up to the shaking of an earthquake. Earthquakes happen when two plates on the Earth's surface rub together, and it causes the ground to shake. It causes the ground to shake. Sometimes it shakes a little, sometimes it shakes a lot. Chances are you do not live in a place that has earthquakes. But if you do, ask an adult what to do during an earthquake so you can be safe. Modern buildings that are built in earthquake zones are designed to withstand the shaking. But how do scientists and engineers build a building that stands up to the shaking of an earthquake? Well, that's what we're going to be looking at today. First thing we have to do is simulate an earthquake. We're going to build a shaker table. And here's what you need. 2 books and... 2 books, 4 elastic bands, and 4 rubber balls. Oh, wait. Okay. 4 rubber balls. All right, so the first thing you do is actually take your 4 elastic bands and wrap them around your books. Put 1 set on one side, 1 set on the other side, till you have that. Then you take your 4 balls and you stick them in between the books, in the middle-ish. area. But you don't want to have them too close to the edges. And now 2 at the back. And ta-da! You've made your own shaker table. What are you shaking, you ask? I will show you. You build a tower. Like this one here that I built out of building blocks. So here's what you do.
You'll need your base to be securely attached to the shaker table. I use painter's tape because it'll come off again without harming the books.
And what I want to find out is just how much shaking this tower can take before it falls apart. Ready? Whoa. And there it goes. And when you've done that, what you do is you be a science maximite and you design another tower. And you tape it down to your shaker table and see if you can make this tower fall down in an earthquake. And if you built it really well, it probably won't. But you don't have to just use building blocks. There's all kinds of other materials you can use. Check out this building, which is really tall, and you'll see there's a cup at the top, and that's for a baseball. Put it up at the top, and that means there's a weight up there. And then we shake it, and we see what happens. Oh no! Oh, there it goes. So that is what we're going to be doing today on Science Max Experiments at Large. We're gonna be making a giant shaker table and putting a giant structure on top and seeing how we design it to make sure it stands up to the shaking of an earthquake. I'm gonna need an expert to help me though. Oh, I know, Anne would be really good at this. Okay, all I need to do is get Anne, and we can start. Oh, come on. There it is. All right.
Hey, Anne, I feel weird. Why do I feel weird?
I think you're a chair.
Well, that's not good. Hold on a second.
Am I good? Okay. Hi, Anne. Good to see you. Here's your lab coat.
Thank you.
So you're from Let's Talk Science, right?
I am.
All about science education, just like us. Today, I need your help to max out our earthquake table. This is the table
This looks
part,
great.
obviously, but this is a tower I've made out of popsicle sticks. So in order to max it out, I've already built a large shaker table. Come on. This is my large shaker table. So it's got basketballs underneath as the 4 balls, but it works exactly the same. Whoa. Okay, so what kind of tower should we make for the shaker table?
If we want something tall, then we'll reinforce it a couple spots. But the true test, it's gotta have some sort of weight on top so that it will mimic the weight that would be on a real tower.
Right, so maybe I could get a plastic bin and I'll just put some sandbags for weight inside.
That would be perfect.
And then balls, so that when it falls over, the balls will go everywhere.
That would be perfect.
Okay, great. Shake off. I don't know. I think we should just get off. Another thing that happens during an earthquake is soil liquefaction. Liquefaction means something turns to liquid. In this case, the very ground you might be standing on. Here's how you can experiment with soil liquefaction. All you need is a plastic container and some water, not very much, barely enough to cover the bottom of the container, because what you're gonna put in next is sand. And you wanna put it in there and spread it around. Just add enough sand so it just starts to turn dry on the very last layer. So here is a house that I'm going to put on top. And now I will simulate an earthquake. The water rises up and it sort of turns to liquid. Soil liquefaction. And heavy things like houses and cars, they tend to sink like that. And then the soil rehardens and everybody's houses are stuck in the mud. Now, let's max it out. This is a giant tub of sand and water, and this is a vibrating platform that will simulate an earthquake. Now, as you can see, this sand is totally solid. I can jump all around on this sand, no problem. But when I turn on the vibrating table and simulate an earthquake, things will change.
The vibrations bring the water below the sand to the surface and cause the sand particles to separate. What was solid now turns to liquid in my simulated earthquake, and I start to sink.
I'm up to my shins! There you go! Soil liquefaction! Hey, look at that! It's totally solid! Woo-hoo-hoo! Soil liquefaction! I'm totally... Uh-oh. You know what I realized? When it stops vibrating, it really becomes solid again, and it's very tough to... Well, there you go. Soil liquefaction. I'm really kind of stuck in here.
So Ann and I have made a large shaker table. Now it's just a matter of designing a building. We use lumber and cut it up, use screws to attach it all together, put a platform on top for a weight, and attach it securely to our shaker table. The building is super simple, just 4 corners and a few planks around the outside. No structure in the middle. And finally, the big heavy weight on the top.
There.
We attach a pole to the shaker table so we can shake from a safe distance and try it out.
Okay, very slow.
Forward.
Let's see how much shaking it can stand with our shakeometer.
That seems to be okay.
Kidding.
Oh no.
We barely start to shake our tower before it collapses.
Oh, that didn't really last very long, did it? It completely folded up on itself. What do we do to fix this, make it better?
I think the easiest thing we can do is to use thicker wood. It'll make it less wobbly.
Okay, sure, let's make another one. High fives. We do have lots of wood, that's a good thing.
Ann and I are trying small improvements every time.
There.
Our last building used thinner pieces of wood. Now we're using thicker wood, which we think will help keep the weight at the top from collapsing the building. Everything else about the design of our building is the same. We put the weight on top and fix our pole, and we're good to go.
All right, you ready?
No problem. Okay. Starting to creak.
But it recovers. You can see it lean, and then it comes back, and it resets.
Definitely doing better than the last one.
Oh, no. I'm impressed.
Uh-oh,
here we go.
But it definitely did better than the first one.
It did better than the first one.
And the thicker wood definitely helped.
But it was really starting to turn.
I think on the next one, we need some platforms in the center to help strengthen it even more.
Earthquake Building 3.0. Thicker wood this time, but with platforms in the middle.
So we're gonna see how well this version works with these middle parts that'll hopefully reinforce.
And they're just like the floors of a building.
Okay, well, let's find out if it's gonna make any difference.
Starting to wobble a little, but it looks pretty good.
As soon as we start shaking, it's really obvious this building is more solid.
Uh-oh, starting to creak. Oh, it's really starting to creak.
The platforms in the middle really seem to improve the structure. You can see it bend all the way over and still recover. But still, it wasn't long before...
Really starting to lean.
Wow, the extra pieces really kind of made it more impressive.
It definitely lasted a lot longer than the other two.
It did, but here's what I'm wondering. Are we going in the wrong direction?
What do you mean?
Well, because if it's really solid, it resists the change.
Okay, I see where you're going with this.
So if we make it flexible, it can resist the shaking of an earthquake.
I think it's worth a shot.
Yeah, okay, let's do it.
Being a chef is my absolute passion. And cooking up science recipes is my speciality. I'm Buster Beaker, and this is Cooking with Science.
Oh, hello. Welcome to Cooking with Science. I'm Buster Beaker. My tuna fish and meatball sub soup is coming along quite nicely. But what will we have for dessert? I know. How about earthquake buildings? Ha ha! It's a building made out of wafer cookies. But the people on Vanilla Street built in the gelatin neighborhood. And the people on Chocolate Street built in the crispy rice part of town. Exciting. Now, here comes the earthquake. Oh no! Oh, it's shaking! Oh, the shaking is come and gone for the people on Chocolate Avenue, and their building is still standing. Now, let's take a look over here on Vanilla Street, and here comes an earthquake. Oh no! Oh dear! Looks like the people on Vanilla Street are going to have to rebuild their building because it's all fallen over and being eaten. Delicious. Buildings can be built the same way, but the kind of soil they sit on make a large difference if there's an earthquake. Shaky, wiggly soil or solid, non-moving soil. So there you go, an experiment you can try at home. Delicious. Well, I'm Buster Beaker, and thank you for joining me on this episode of Cooking with Science. Now to try my soup.
Seismometer in 60 seconds.
Learning how to predict and measure earthquakes is an important branch of science. The Earth is shaking, but which way did the earthquake come from? It's all about measuring the vibrations, and to do that, you need a seismometer. All you need is a ball, some paper cups, some modeling clay, a pencil, and science tape, which is the same thing as invisible tape, except I use this tape for science. First, take your pencil and stick it straight down into the modeling clay. Then, you take your cups and you arrange them in a circle and tape the cups down. And that goes right in the middle, just like that. Now what you do is you take the ball and you carefully balance it on the pencil. Now you have created a seismometer. It will tell you what direction an earthquake came from. Watch, I will be the earthquake. Ready? Did you see that? The ball fell into the cup facing the direction that I hit the table. And now I'm gonna hit the table from over here. Yep, it fell in the direction that I hit the table. Okay, let's try from over here. There you go, your very own seismometer that you can use to measure earthquakes that you create on the table.
Back to our earthquake building. Ann and I tried a few different designs, and they each got a little better. But now we're wondering what would happen if we built the tower out of very flexible material. We used some plastic tubing and attached the wood with bungee cords, which are like big elastics.
Wow, okay, so looks good.
So let's test it.
Okay.
And sure enough, when we start shaking it, the tower holds up to as much shaking as we can give it.
Wait.
What?
Aren't we missing something?
Oh. Yeah, we're missing the weight at the top. Of course.
So I think we need to try it again.
So we add the weight to the top, and then everything changes.
Oh, no.
Look at it twist.
Oh, dear.
It's twisted.
A flexible tower is great until you try to put a weight at the top. And then it just seems really unstable.
Oh, look at that. It's totally bent.
It didn't break at all. It just fell over.
Yeah, it couldn't even support the weight.
So it was almost too flexible.
So I guess we should go back to a more rigid design. But what if we change the shape a little bit? 'Cause you know what I was thinking? This is a very stable shape. Triangle, because triangles are really strong. What about we make an X?
Like a triangle within a triangle.
Triangle, and then triangle. So that really reinforces all of the shaking, like all of the motion.
We'll never know until we try.
All right. Uh-oh. I have all my friends coming over, and I don't have a table. But that's okay. I will make a table using my friends. This is an awesome experiment you can do with 4 friends. Come on in, science friends. I've got Sam and Dylan and Polly here to help me. So everybody turn to your left and sit sideways on the chair, and then scooch the chairs into the middle. And then everybody leans back onto the knees of the other person. And then, this is why I said you need 4 friends, because you need the 5th person to remove the chairs! Oh. The reason why this works is because everybody's weight is being supported on the legs of the person next to them. Okay, we're gonna rotate in a circle, everybody. Okay, ready? Here we go, rotating, rotating. Oh, science table. Ooh, hey, we're pretty good at this. Okay, uh-oh. Oh no, oh no! So there you go. Awesome way to make a table using your friends. Well done, science. Here's an experiment you can do to impress the adults in your house. You need 3 glasses, all of equal height, and 3 knives, not sharp knives, the dull knives you use, maybe the ones you use at dinner time. Take your 3 knives and put them in a triangle, all equally spaced out. Then move the knives together to make a little triangle, right like that. Then what you want to do is you want to carefully arrange the knives so each knife is going above one knife and below another knife. So there we go. Then you want to take this careful pattern that you created and you want to put it on top of your 3 glasses. One where each handle of the knives are going to be. And if you place it carefully and you've done the over-unders correctly, it will stay up. Pretty amazing. The knives support their own weight, but they don't just support their own weight, they can support a lot more weight too. Pretty amazing, right? This is a great experiment. It's also something really interesting that we can max out. Come on. And here you go, the maxed out knife balance. I've got 3 pieces of lumber and 3 barrels, and as you can see, the pattern is exactly the same. Under, over, under, over, under, over. Ha-ha. So, the question is, how much faith do I have in science? It totally supports my weight. I know it's going to work because I know that a 2x4, which is the kind of lumber I'm using, can hold up my weight. So that means the structure can support me. Science! You know what the cool thing is? The cool thing is that even though it's holding me up, each one of these pieces of wood is only up because it's supported by the others. You pull one out and it all falls apart.
Ann and I have tried solid towers and flexible towers, and nothing has worked fantastically yet with a big weight on the top. Having a big weight on the top of our tower means we need something that will resist the movement of that weight. So now we're going to start with a triangle. Unlike a rectangle, triangles are very stable. A wider base keeps the structure from swaying too much. And cross braces in the middle mean that there are other triangles within our triangle, all the better to resist movement.
Thank you.
After Ann and I built our tower, we added the weight to the top, secured it to the base, and tried it out.
Okay, here we go.
Ooh. Looking good.
No problem.
It's not twisting.
It's
not even leaning.
Not even creaking.
No, it looks really good.
Wow, this one is really solid. As you can see, this tower is way more solid than our square tower or the flexible tower.
Okay, look at that. Like, if that's not an earthquake, I don't know what is. Look at that. Look at the way the ground is moving.
I don't know if we can shake it much more than this.
Faster.
Our triangular tower is up past a level of shaking that made the other towers collapse. Now it's time to max out the shaking.
There's only one level of shaking that we can do above this.
What's that?
We shake from either side.
We give it all we have. The floor was bouncing from side to side, the tower was tilting, and was totally solid.
It's still holding strong.
In fact, Ann and I wore out before the building showed any signs of falling over.
I think we've done it.
Woo! Nice.
Yeah. Nice. Science Max experiments at large, earthquake-proof building. I mean, come on. That was impressive.
I like it.
Here is an invisible tower. Huh? I escaped.
I'm just preparing my... I forgot my line. Hello. Just gonna add some more salt to the soup. Delicious.
Well, humans have been figuring out ways to figure out just that. I said figure out twice. I'm gonna start again. Okay.
English is not my first language.
I guess those are staying in there.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have.
Yeah!
My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max!
Try yours.
Here we go. What makes airplanes, or basketballs, or people fly? It's air. As well as a bunch of other things that we learn when we try to make a giant paper airplane.
So that didn't work.
All on this episode of Science Max, Experiments at Large.
Greetings, Science Maximites. Today, we're going to be looking at air. I know, it's kind of hard to look at air because it's invisible. But we can look at something that uses air to move. That's right, paper airplanes! Ha-ha! Ho-ho! Look out! Woohoo! Believe it or not, you can learn all kinds of science from paper airplanes. So let's build some. We are going to do a paper airplane which actually holds the Guinness World Record for the longest paper airplane flight. Pretty cool, huh? First, you fold the paper in half like this, but then you open it back up again, and then you fold in the corners like this. Now, don't worry if this is really, really fast because you have all the instructions on our website. Then you can fold the paper down like this, make sure it's about 2 centimeters from the bottom where the point is there, and then you fold the corners in just like you did before. But these ones are just guide folds. We use guide folds to help us fold other folds, basically. Now, we fold again using the guide fold lines you just made. And I like to call this fold the shirt collar fold because it sort of looks like a shirt collar when you fold it. Now, we fold again on the fold that you made before. Folds in like that and in like that. And now we fold the point down to touch the edges right like that. And this is a guide fold, so do it very strong. Unfold it. Now you fold it in half like this. And see that guide fold line that we made there? What you're gonna do is you're gonna take the tip and you're gonna fold it in to touch the guide fold line like that. And this is also a guide, and open it up. And here's the trickiest part. See how it's bent like that? You push it open like this, and this is called a pocket fold because you wanna make a little pocket and push it up against there. Fold it flat like this. Fold this tip down over there like that. Then fold it around the back side. Then fold the wings down like this and like this. And here's the extra special bit. We're gonna use some stabilizers on this plane. Fold up the stabilizers on the ends of the wings and ta-da, the Sky King paper airplane fold. Now, as Science Maximites, you know that there's lots of ways you can learn how to fold paper airplanes. Get an adult and look up paper airplane designs on the internet, or take a book out of the library on how to fold paper airplanes. And of course, this isn't Science Max, Experiments at Large, if we don't max it out. So that's right, we're gonna make a giant paper airplane. I'm going to the Ontario Science Centre to do just that. Uh-oh, that's never good.
Whoa, Phil, I'm so sorry, you okay?
Yeah, I'm okay, Justin. I never know where the portal's gonna spit me out. This is the Science Center, right?
Well, that's right. In fact, you've landed in our paper airplane laboratory.
This is what happens to me, Justin. I make a paper airplane, I fold it perfectly, but then it flies like that, or it does that, and I don't know how to fix it.
Okay, well, that will happen. But you know what? There are really only 3 ways your paper airplane can fly, and I can teach you how to control each and every one of them.
Great, let's do it.
Let's do it.
All right.
Science Max presents How to Fly Your Paper Airplane. Is your paper airplane spinning around and around? Well, that's what you call roll, chum. Roll is what you call it when any plane moves like this or like this. Here's how to fix it. Bend up the back of one wing to create more lift on one side, and it'll balance out. Happy days.
Okay, so let me try mine.
What's that? Your airplane goes straight up or straight down? Sounds like you have a problem with pitch. Sorry, pitch. Pitch is when your airplane moves like this or like this. To fix it, bend the ends of both wings up if you pitch down, or down if you pitch up. Adding a weight to the nose also helps if you've got a problem with high pitch. High pitch.
Great, your turn.
All right, here we go.
Is your plane turning this way or that way? Yeah, Ya? No, ya. Ya is when your plane moves like this or like this. To fix it, bend the back of the plane like the rudder of a boat.
Okay, great. Let me try mine. Not bad. You try yours.
Real?
Oh, yeah.
That was pretty cool.
That's what we want.
Yeah.
You know what? Are you ready to build a giant paper airplane?
I think I am.
Fantastic. I just need to get one more expert. I will be right back.
Cool.
Hey, David, how you doing?
Hey, good.
Good. So David's going for his Masters of Applied Science.
In aerospace science and engineering.
So you know all about planes.
I do.
Great.
Yeah.
So what does this have to do with planes? What is this?
So this is a water channel, and it allows us to test airplanes in it before we put them in the sky.
Great. We'll have my airplane, and we'll just put it in here, and we'll test it.
Please, it's made of paper.
Yeah?
And in the water, it becomes soggy.
Well, how do we test our paper airplane if we can't put it in the water?
Well, this is a classic airfoil shape.
Yes. Now, is that what you call it, airfoil?
An airfoil, yeah. So the cross-sectional shape of a wing is called an airfoil.
Okay.
And that's what generates the lift. Fortunately, air and water are both fluids, so they behave in the same way. I could push ink into the water, and that's going to allow us to see how the fluid flows over the aircraft. So if you tilt its nose up a little bit, you'll be able to see that the shape of the airfoil is actually pushing the water downwards.
Oh, yeah, you're right. The ink doesn't go straight. It follows the wing down.
It follows the shape of the wing down, and we have a lower pressure on the top of the wing and a higher pressure on the bottom of the wing, which pushes it upwards.
Right,
generating
and
lift.
that creates lift.
Exactly.
So you guys use this all the time in aerospace?
Yeah, yeah.
That's pretty
Absolutely.
neat. So, are you ready to design an even bigger plane, a giant paper plane?
I'm confident we can do a good job.
I am excited about it. Let's do it right now. The big paper's over this way. This way. Okay. Here's the plan. Take a giant piece of paper and fold the exact same airplane we did in the lab. The small one flew. The large one should too, right? Well, let's find out. I believe we are ready to make our giant paper airplane. All we need is a giant piece of paper! Okay, be very careful getting off it. All right, let's fold it. Nose on that side. Okay. Remember, we're folding the exact fold we did in the lab, only on a larger scale. We have a tape malfunction down here. But it's a lot harder to do with a giant piece of paper.
Fantastic. That's pretty good.
Okay. There.
Perfect.
Yeah. Giant paper airplane!
This doesn't look too much like an airplane.
No, it's way too floppy.
Yeah, but I mean, maybe it just needs, like, when I throw it, maybe it'll catch the winds, and then the wings will come up like that.
Yep. Maybe.
Like, you know, I'll just...
Give it a try, Phil.
Okay, I'm gonna give it a try. Giving it a try. Okay, you guys ready?
Yeah.
Go for it.
Okay, here we go. Wow. What do you think?
Oh man. I think we can make some improvements.
It sort of felt like a bed sheet. I feel if I just threw my lab coat, it'd probably look. Let me just see. Okay, ready? Yeah, it looks pretty much the same, doesn't it?
Yeah.
So, I didn't know this, but when you fold paper that big, it sort of behaves like fabric.
Yeah, very floppy.
Very floppy. What if we supported the plane, like we put struts or something in it, like this stick? If we put it on the wings, it'll stop it from being so floppy.
Right, and you can tape it on.
Yeah.
That's a great idea.
Yeah.
We need bigger sticks.
Yeah.
Really lightweight.
Like
like
foam.
Yeah.
Stuff?
And like hollow tubes.
Hollow tubes.
Good.
Good. So we'll put a whole bunch on there. We'll tape them on so that it doesn't flop around.
Yeah.
We'll try it again.
Yeah.
Yeah, I think we got something.
Okay, great. Let's go.
All right.
Bernoulli's theorem states that faster moving air has lower pressure than slower moving air. You can demonstrate this yourself with a ping pong ball and a hairdryer. You put the ping pong ball on the stream of air from the hairdryer, and because it's moving quickly, it has lower pressure than the air around it. So the low pressure air works sort of like a force field, and you can defy gravity with your floating ping pong ball. Awesome! But of course, this is Science Max Experiments at Large, so we have to max it out with a giant hairdryer and a giant ping pong ball. Sorry, I said science! You probably couldn't hear me because of the... So, our giant paper airplane turned out to be really floppy. When paper is that large, it doesn't hold together very well. What we're going to do is take foam and long sticks and tape it to the large paper airplane wherever we need to give it support. So, here, and here, here, and a bunch there, and maybe some over there. Well, it turned out we needed to reinforce in a lot of places.
There. And then that.
Great, look at that. It's not even flopping around. It stands under its own weight. Huh?
There's a whole bunch of stuff on it. I don't know if it's gonna fly so well.
Oh, it's gonna be. Well, I mean, I have to put the stuff on it so it doesn't flop around.
But there's like really a lot of stuff.
Well, I needed this foam to reinforce this foam, and then I needed the cardboard to reinforce both of those.
Phil, there's a giant hole in the wing.
Well, I can fix that. Just move your head, and then I'll just.
Phil, there's a lot of stuff on here.
There.
But like, it's really a lot.
Problem solved.
Guys, let's just fly it.
Oh, okay, sure, yeah, let's do it. Let's do it. All right.
Okay. All right, here we go.
Maiden voyage of the Mark II giant paper airplane. Okay, here we go. 1, 2, 3. So it went about 3 feet. So that didn't work.
I told you, too much stuff.
You did. He told me that.
He said that.
He said that.
What we need is something that's stiffer without as much stuff on it.
But the paper, it's too floppy, so you have to put the stuff on.
Right.
How about some cardboard? Cardboard's nice and stiff, and technically it's paper.
You're right, cardboard. Let's make it out of cardboard.
Yeah.
Cardboard, all right. Oh, it's over here. Tornadoes are giant weather systems that cause the air to go around and around. Tornadoes can be pretty dangerous, but they don't happen that often. Here's how you can make your own small pet tornado you can play with at home. Because air and water behave similarly, we can make a water tornado. You spin it around, get it going, and ta-da, your very own pet tornado. Here's how you do it. You take two 2-liter plastic bottles and fill one with water and some blue food coloring, is what I like to do. And then tape the mouths of the bottles together. You might need an adult to help you with this because you want to make sure the bottles are perfectly aligned. Then flip it over, spin it around to get it going, and voila, your very own pet tornado. Awesome. And now we're gonna max it out with a giant tornado chamber. Hey, Michaela.
Hey, Phil.
So this is your giant tornado. It's amazing.
Yeah.
So I made one with plastic bottles and water, but this one uses air, just like real tornadoes do in the wild.
That's right.
So how does this work?
Well, here we have a platform, but underneath that there's a fog machine that's pushing the fog up. And we've created an updraft because there's a fan at the top that's pushing air out of the top. And also we're trying to mimic the intense winds you'd get from a tornado with these pillars that are shooting out air in this direction.
So it goes around in a circle.
Yeah, in real life, tornadoes are pretty rare. You need a perfect set of conditions to see them. You need warm, humid air and cold, dry air. And as well, some intense winds that you usually get from thunderstorms.
Science! If I was to drop this light basketball and this heavy workout ball at the same time, which do you think will hit the ground first? Let's find out. They landed at the same time. That's because everything falls at the same rate. It doesn't matter how heavy or how light something is. Until things are falling fast enough that air friction or drag starts to play a factor. Soon, things reach their top speed. This top speed is called terminal velocity. It means I could throw this basketball from an airplane and it might not be going any faster than if I threw it from, say, 10 stories up. I'm gonna find out what the terminal velocity is for both of these objects when we max this out. Ninja science roll! Here's how terminal velocity works. Everything falls at the same rate, going faster as gravity pulls it down. But when things start going so fast that just pushing through the air at that speed creates as much force as the pull of gravity, things reach a top speed and they won't go any faster. How heavy something is and how much air it pushes both play a factor in its top speed. And that top speed is called terminal velocity. How cool is that? I'm at iFly Toronto. This is a giant wind tunnel, and they've got the wind going fast enough that they can't fall any faster. It's the terminal velocity for a human being. I'm gonna take our weighted ball and our basketball and place them both here in the wind chamber. This is the control panel, which is what they use to control the wind speed inside the chamber. And this is Derek, who's gonna be operating it. And that is Mike and Greg, and they're inside the chamber. All right, let's fire it up.
All right, firing it up.
35, 58, nothing happening yet. This number here is the one we're looking at to see how fast the air is moving. 86, something's starting to happen. Oh, 89, wind speed of basketball, 89 kilometers an hour. At 89 kilometers per hour, the wind is going fast enough that the friction of the wind and the pull of gravity balance out, making the basketball float. This means you could throw a basketball out of an airplane and it would never go any faster than 89 kilometers per hour. All right, let's keep increasing the speed. 106, 124 kilometers an hour, 140, 150. Oh, 166, almost. 172, whoa. Wind speed of the heavy red ball, 173 kilometers an hour. Because the red ball is heavier than the basketball, we need a lot more wind speed to counteract the force of gravity before they cancel out and the ball floats. Here's something else that's going on that's cool. Mike is flying, but Greg is not. That's because Mike is lying down, which means he's catching a lot more wind than Greg is, who's standing straight. If Mike stays lying down, his terminal velocity is the same as the red ball, 173 kilometers per hour. But Greg's velocity would have to be a lot faster. And that's science! So the giant paper airplane hasn't been working so well. The problem is paper can't hold up its own weight when it's that large. Cardboard is much stronger than paper, so we've decided to rebuild the plane out of cardboard.
All right, Phil, hoist it up.
Then we take it to the roof of the Science Center and see if we can get it to fly. Oh, woo! There you go, our Mark III model paper airplane. Now, I know it's made out of cardboard, but cardboard is technically paper, and it's the only thing strong enough to hold a plane of this size together. We even had to put some poles in so the wings still wouldn't flap, but we're pretty confident this is gonna work. Okay.
All right, Phil, we're in position.
Now, don't try this at home. Our roof has a big wall on the edge. Your roof does not. Our first attempt didn't go so well. Looks like we have a bit too much pitch. Our second attempt still had a bit too much pitch. Time to add some weight to the nose. We added some clips to the front to give it a little bit more weight on the nose, which is important. Although at this point, I kind of wish there was less weight. Whoa, okay, all right.
Phil, that was great!
Woo! All right! Woo! This throw worked best, but I know what you're thinking.
Why didn't it sail through the air like a normal paper airplane does? Well, that's because the other thing heavy planes need to fly is thrust. So we could put an engine on our plane, but then we'd have to use something stronger than cardboard, and well, pretty soon we'd have an actual plane. But this isn't about making a full-size plane. This is...
Largest paper airplane I've ever thrown! Woo! You guys are great! The plane is great! Thank you very much for watching Science Max Experiments at Large. Where were the stairs? Yeah. Oh, never mind, I found them.
Science Max is a show where we take small experiments and do them big. If you want to try these experiments yourself, go to our website for instructions. But not all the experiments on Science Max are the kind you should try at home. This one, yes. This, no. Try this, don't try this. A big yes, a big no. I don't know how you could possibly do this one at home. And remember, if you're ever not sure, ask an adult. Thanks for watching Science Max Experiments at Large.
Does that sound like music?
Sounds good.
Stop!
Yeah.
Yeah.
Yeah?
Yeah.
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 Word has lost all meaning. Science!
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max Experiments at Large. Science Max! Electromagnets are magnets you can turn on or off when you want. We build our own electromagnet and see just how powerful we can make it.
It held 100 kilograms.
Plus ferrofluid, wizards, and I tried to get to the North Pole using a compass.
Now that I'm here, I realize it's really difficult.
All on this episode of Science Max Experiments at Large.
Greetings, Science Maximites. My name is Phil, and welcome to Science Max Experiments at Large. At this very moment, half the lab is being held together with the power of electromagnets. And Magnet 1 turning off. Electromagnets are a really cool and powerful way to interact with the world. And when I say power, that's because you need power to make them work or not work. Magnetism is an invisible force that has to do with the magnetic fields created by magnets that lets them attract things that are metal or each other. But electromagnetism is a little different. You see, magnets are magnets all the time. It's because of what they're made out of. Electromagnets are only a magnet when you have an electric current going through them, which means you can turn them on or off. Today, we're gonna be building an electromagnet. Oh, that was the wrong switch. Anyway, like I was saying, today we're gonna be building an electromagnet.
You need a bunch of copper wire, a very large nail, or something metal to become your electromagnet, electrical tape, a battery, an on-off switch, wire strippers or a craft knife, and the help of an adult, and finally, something to magnetize, like these paper clips. And remember, all of the steps for this experiment are on the website. To begin, take the copper wire and start at the top of the nail. Leave a little bit of wire sticking out, then carefully start to wrap the wire around the nail. Don't go all the way to the end because you need some metal to turn into the magnet. Instead, when you want to start again, run the wire straight back to the top and start wrapping again in the same direction.
And keep wrapping and wrapping until you get to this. Now, I've used some electrical tape here, here, and here to hold it all together.
Using your wire strippers or a craft knife and the help of an adult, remove the plastic coating from the ends of the wires. Attach these wires to the wires from the on-off switch with electrical tape, or attach them directly to a battery if you don't have an on-off switch.
And ta-da, you have an electromagnet with your on-off switch. All you need to do is take the things you're going to magnetize, turn your electromagnet on, and suddenly it becomes a magnet. Pretty amazing, ha 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 ha. And then you can magnetize to your heart's content. But when you're done, don't forget, you want to turn it off. So that's what we're gonna do today on Science Max, Experiments at Large. We're gonna max out the electromagnet. So, where's my lab coat? Oh, there it is. We're gonna see how big we can make an electromagnet. And when I say we, I mean me and an expert. Let's see. Oh, Heather from the Ontario Science Center. She knows her way around magnets. So let's see. Yeah. I wonder if she's busy. Well, let's find out. And after we're done, I'll need to come back and clean up the giant mess I made in the lab.
Hey!
Hi, Heather, how you doing?
Good to see you, Phil.
I was just wondering if you could help me with something. Are you busy?
No, I got time.
Okay, great, because I'm gonna make a giant electromagnet experiment and I need your help.
That sounds like a lot of fun.
Okay, great. Let's go back to Science Max headquarters.
Oh, via the portal?
Yeah, by the portal.
Oh, okay.
You sure? I
yeah.
know you're hesitant, so I want to reassure you, nothing will go wrong.
Great, okay.
Okay. Oh, hey, we're here.
We're outside.
It's okay, it's
no,
okay.
no,
Don't worry about it.
no,
No,
I
no,
think
it's fine,
definitely.
it's fine.
You all right?
Yeah, I was supposed to come in over there, but I came in over here. Oh well. So today, Heather, I want to max out the electromagnet. Turn it on, and it's a magnet.
Pretty good.
And turn it off, and it stops being a magnet. I want to make this into a much bigger, maxed out version.
All right.
So what are some of the things we can do to do that?
Well, actually, if you have a larger battery, one that has a higher voltage, we can try that for sure.
Okay,
that
so
will help.
there are batteries that are 12 volts?
Yes.
We could try one of
Give it
those?
a try,
I think
for
those
sure.
are like bigger, right?
Yeah, bigger, more powerful, absolutely. Now, that's one thing you could do. You can also increase the number of wraps of our coil here.
So how many times we wrap that wire?
Yes, we'll increase that magnetic field, making our magnet stronger.
And of course the nail, which is important because that's the thing that eventually becomes the magnet, right?
Right on, yes.
So what I thought we would do is we would start with a bigger nail.
Oh.
What, right? So larger battery.
Yes.
More voltage and a lot more wraps of the wire.
Right on, and we have more space for that now, which is smart. Good job.
Great, okay, so we'll get to work.
Great.
Max Historica.
If you've ever seen a compass, you know that the needle points north. That's because a compass needle is a magnet and it points towards the Earth's magnetic North Pole. And I'm using this compass to try to get to the North Pole. But it isn't easy. In fact, scientists knew there was such a thing as the North Pole as far back as the 16th century. But no one was able to actually get there on foot until 1927. You'd think it wouldn't be that hard, right? I mean, the needle points you straight there. Just follow the needle, right? But now that I'm here, I realize it's really difficult. I mean, the wind is incredible and the snow is intense and it's so cold. My hands, yeah. So, okay, we're not really at the North Pole. We were just sort of recreating that. But still, I salute the brave explorers who tried to make it there in the name of science. And I got a sense of it because the wind from the fan and the fake snow was. Okay, everybody, let's pack it up. I mean, that was pretty good. I just didn't know about that other camera.
So, back to our main experiment, where Heather and I are building a larger electromagnet. An electromagnet works like this. When an electric current is traveling through a wire, it creates a magnetic field. If you wrap that wire around something ferromagnetic, that's something made out of a metal that is attracted to magnets, like an iron nail, then it becomes a magnet. You can make a magnet stronger by wrapping more wire, which gives more distance for the current to travel, increasing the magnetic field, and you can also increase the strength of the current. Heather and I start with a coil of 30 meters of wire and start wrapping. And wrapping. And wrapping.
There, the wire is now all done. And remember, if you're doing this at home, do not use a drill unless you have an adult to help you out, because drills can be very dangerous. This one goes at a very slow speed, so it was okay. But yes, definitely an adult supervised activity.
Then we attach another on-off switch and make some leads that connect to a 12-volt battery. So, more wraps of wire and more current means the electromagnet should be stronger.
Okay, so we're gonna try this electromagnet, and we're gonna pick up this stuff right here.
Great.
Ready?
You ready?
Yeah.
3,
2, 1, go! Is it on?
Yeah.
Wow, it really does, you can't tell it's on, but...
No, but bring it closer and...
Oh yeah, look at that. Okay, we turn it off.
All right.
Let's see if this nail can pick up this nail.
All right.
Ready?
Ready?
Go. Oh. Okay, how about this side? Oh, no. No.
I don't think we're strong enough.
It's not strong enough. I think that we need to max this out even more.
Even more?
Right.
So I'm thinking there are a lot of appliances that use electromagnets, meaning it's already set up, it already has tightly wound coils and high voltage. So we're in a lab here. Maybe do you have old appliances around?
I have parts bins with a whole bunch of stuff. Maybe we could find some electromagnets in those.
Let's do it.
Okay, great. Let's go. All right, pliers, battery, copper wire. Now, if you've already done the electromagnet experiment, here's another experiment that uses all the same materials, plus these. Ha! Neodymium magnets, some of the strongest magnets you can get. So, here's what you need.
A battery, some neodymium magnets the same diameter as your battery, copper wire, and some pliers.
So here's what you do. First thing is you put the batteries and the magnets together, like that. Then what you want to do is bend the wire so it's touching the top of the battery and goes around the battery and then touches the magnets at the bottom. Here's what that might look like. I say might because you can do any shape you want. I've made a coil here, and if you put it over the battery, you'll see it only touches the very top of the battery and the magnets at the bottom. And if I let it go, it spins. It's a homopolar motor. What happens is the battery sends an electric current through the copper wire, and that turns it into an electromagnet, which is attracted to the magnets at the bottom, and it spins. So, now, let's max it out. Aha! A D-cell battery, which is larger and, of course, larger neodymium magnets. And you do the same thing. Make a coil that only touches the battery at the top and at the magnet, and ha-ha! It spins! Maxed out homopolar motor. But don't worry, this is not the biggest size we're gonna do. Come on. Maxed out homopolar motor. I have 27 D-cell batteries, a giant copper tube, and a neodymium magnet. So I'm just gonna, and then we get rid of that. Put this down. Okay, so the first thing I do is attach the neodymium magnet to the batteries. And I've got all the batteries taped together here so they'll sort of stand up like this. Huh? Giant stack of D-cell batteries. Okay, now what I do is I take the copper coil. I take the copper coil. I need to get. Okay, hold on. I got this. I just need to get the copper coil there. I did it. Okay, so I take the copper and I put it on top of the D-cell batteries like this, and then I let it go. Let it go. Nope, whoa. Homopolar motor. Okay, so that didn't work. But that's okay. I like it when it doesn't work, because that's science. It's not science if it works perfectly every time. I mean, you gotta have some room for improvement. Heather and I built a larger electromagnet, but it still wasn't as powerful as we hoped. So now we're searching for parts that came out of an appliance that are pre-built electromagnets. What about this?
I think that'll do the trick.
Do you think that does look like an electromagnet, huh?
It does, yeah.
And there's a whole big bunch of copper wires coiled on
Coiled
that.
around.
So you think we can use this?
Yeah, let's try it.
Okay, great. We built the next version of the electromagnet. This one already has the copper coils, so it's just a matter of attaching wires and an on-off switch, and attaching all of it to a 12-volt battery. Do you think 12 volts will be enough?
Let's find out. I think so.
Try that. Once we do, it works much better. Oh, no problem at all.
Ready?
Yep, turn it on.
On.
Whoa, pretty good. Okay, off.
Off.
Neat. In case it was really strong, I have the next step. Horseshoe. Okay, ready? Oh, whoa, that's...
Here.
I can't pull that off. Okay, wait, grab this. Okay.
Work together.
Yep. So that's passed all of our tests.
Yeah.
This is really strong.
Is there a way to test it further?
In order to test how strong our magnet is, it's as easy as seeing how much weight it'll lift. Heather and I find a metal table.
All right, Phil, so I brought the electromagnet.
Okay.
Just put it right here.
Yep. We add some sandbags for more weight and then attach a scale so we can measure how much weight we're lifting. We use a chain hoist, a simple machine made for lifting heavy things. This one can hold up to 454 kilograms. Want to turn it on?
All ready?
Yep.
Here we go.
You can read on the scale how much weight is being lifted.
And that scale is going up.
Pounds on this side, kilograms on this side. We keep lifting until... Oh! Okay, so how much did it hold?
It held 100 kilograms.
Oh, that's more than I weigh, which gives me an idea. Come on. This is ferrofluid. It is ferromagnetic, which means it's attracted to magnets. And I know what you're thinking. You're thinking, it's not that interesting. Well, watch as I put it next to this magnet. Very interesting. And because it's a liquid, it behaves in very interesting ways. Watch this. Unlike most things ferromagnetic, like paper clips or iron filings, ferrofluid is a liquid, which means it behaves in a unique way. The spikes it creates are following the magnetic field lines of the magnet. You can see the magnetic field in 3D. It's even more impressive when we max it out. This is ferrofluid outside of a glass jar. Now, it's sitting in a pool around this electromagnet. And this is a dial which I can use to change the voltage of the electromagnet, making the magnet stronger. Watch this. Changing the current going to the spiral in the middle turns it into a magnet. The more current I put in, the stronger that magnet becomes, allowing the ferrofluid to climb the spiral to the top. And remember, even though it looks all spiky, it's still a liquid. I will demonstrate with my plastic spoon. And watch this. When I turn the magnet off, it stops being spiky. Turn it on. Turn it off. Science.
The Wizard Academy. All you have to do is demonstrate true magic. And you will be granted entry.
Well, Fuzzix, who is the next applicant for the Wizard Academy?
Overwhelmo.
Indeed, it is I, Overwhelmo. And prepare to be overwhelmed. Would you be flabbergastified if I balanced this coin on its end? Not really, no. But would you be impressed if I was to balance this coin on top of this coin? Possibly. Prepare to be flustered and stupefied. stupeflustered as I balance 3 coins on their ends on top of this glass.
Well, that certainly would seem like magic. Let us see.
Okay. No pressure, Overwhelmo. You can do this.
And now, I say, a magic word.
A magic word! Ha 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 ha! And now you must let me into your academy.
Wait. What's under the cloth?
What cloth? This cloth? Nothing. Oh!
Is that a magnet?
This? No!
The pull of the magnet is what's keeping those coins up. The magnet is just strong enough to keep the coins from falling.
No, this is set dressing. It's just...
It was a good trick, but it's science, not magic.
Well, yes. And you will see! You will see! I will be back! I, Overwhelmo, will return! And I will do such magic that you will need extra socks. Because I will knock them off! With my magic, you will need at least 2 pairs of socks, maybe 3 pairs of socks.
We can still see you!
No, you can't!
So back to our main experiment. Heather and I have created a very strong electromagnet that can hold a lot of weight.
It held 100 kilograms.
Oh.
Which gave me an idea.
All right, you ready?
Let's do it.
Electromagnets super maxed out experiment. We've got
2 electromagnets, 1, 2.
And those are wired to 2 batteries, which are on my belt, just like this, so that I can carry them around. And we've got a crash mat here, because
we need to keep you safe because you're going to be using these electromagnets to get across this massive beam above us.
That's right. I'm going to stick to this metal beam and go across with the electromagnets.
Wow.
We hope.
I have faith.
I'm glad you do. I've got a helmet for safety, goggles for safety, gloves for safety, but in this case, sometimes the lab coat is more safe and sometimes it's less safe. This time, it will get all caught up, so no lab coat. All right, you ready to go?
I'm ready. Let's do it.
Okay.
My goodness. 1.
Okay.
Because each of our electromagnets can hold more than my whole body weight, I can use them to cross the beam. When they're on, they stick like, well, magnets. And when I turn them off, they stop being magnets and I can move them along as I go. Now, this is something you should definitely not try at home.
Come on, Phil. You're almost there.
We did it! Yeah! There you go, Science Max, experiments at large, electromagnets! Woo! You want to go?
No.
You sure?
I'm positive.
Okay, I'm going again. Woohoo!
Crazy.
Oh, careful. Don't mess it up, Overwhelmo.
Overwhelmo.
Send in the next applicant for the Wizard Academy.
Overwhelmo.
And now, I say the magic word.
Overwhelmo.
I say the magic word. The magic word!
Well, that certainly does seem like magic, yep.
As I balance not 1 coin, not 2 coins. That's a 3.
Have you ever done a science experiment and wondered what it'd be like if you did it big? I have. My name is Phil, and I take your everyday science experiments and do them big. This is Science Max, experiments at large. Science Max! Today on Science Max, we're looking at chemicals. Chemicals make up everything around us, and we're finding out which ones you can mix together to make spectacular science.
Whoa! Woo! Cutest science ever.
Today on Science Max, experiments at large.
Greetings, Science Maximites! My name is Phil McCordick, and the name of the show is Science Max Experiments at Large. Today, we're taking a closer look at chemistry. Ooh. Chemistry is the science of atoms and molecules, the things that make up all matter, and how they interact with each other. Take, for example, this glow stick. Actually, don't take it, because I kind of need it. The glow stick doesn't glow until you... The glow stick doesn't glow until you break the barrier and mix the two chemicals, and they start to glow. Huh? Pretty cool, huh? Chemistry. Now, the chemical reaction we're looking at today is the old vinegar and baking soda volcano. But this reaction doesn't have anything to do with volcanoes. It's chemistry. Now, this experiment is totally safe, but I do recommend you get an adult's permission before you do it because it's very messy. Yeah. First, you're gonna want baking soda and vinegar. These are your two main ingredients, but you'll also want dish soap and red food coloring if you want it to look a little bit more like lava. Now, I like to mix the baking soda, red food coloring, and dish soap together with a little warm water, so all you have to do is add the vinegar. And when you do, this is what happens. And there you go, chemical reaction. Now, I know what you're thinking. You're thinking, Phil, how much vinegar or baking soda do I use? Well, I'm not gonna tell you. This is where you can be science maximites. Try different amounts. More vinegar, more baking soda, more dish soap. Who knows? Write down the amounts each time you use it and find out what amounts work best. That's called science. And that's what we're gonna be looking at today, chemistry in all its forms. And of course, because it is Science Max, experiments at large, we're going to max out the vinegar and baking soda volcano. So I'm off to the Center for Skills Development and Training. Come on. Hey, Talina.
Hi, Phil.
How you doing?
Good, how are you?
Good. This is Talina. She's going for her PhD in chemistry from McMaster, right?
Yep.
Awesome, which means you can help me max out the baking soda and vinegar. We need vinegar. You grab that vinegar. And vinegar volcano. So what happens when we mix these two chemicals?
Well, vinegar is an acid and baking soda is a base, and when you mix them, they neutralize each other to produce carbon dioxide and water as a byproduct.
So acids and bases are kind of like opposites.
Yep.
So I guess that makes sense. When you put them together, crazy stuff happens.
Yeah.
Awesome, chemistry. Okay, so I want to use this much vinegar and this much baking soda.
What's with the fish tank?
The fish tank is where I want to mix it all together. What do you think?
Awesome.
Maxed out. Okay, let's move the fish tank somewhere where we won't make a huge mess. It's a little heavy with all that. We're gonna, no, we're gonna have to take a couple trips. That's kind of heavy. Okay, so we'll take this and that, and then this, and that. No, hold on. I can do it. Just one more. Okay, good. Okay, good. Yeah. I took too much. I took too much. Uh-oh. Uh-oh. That's good, Ramona. Put it in the background. Put the sign in the background. Yeah, in the BG. I love the BG. Chemicals. 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 Chemicals? Chemicals. What are chemicals? Are they things you have in a lab in a jar that say chemical on them? Well, yes. But if that's all you think chemicals are, then you need to know your chemicals. Turns out the stuff in the jar is a chemical, but the jar itself also made of chemicals. The table I'm putting it on, made of chemicals. My lunch, chemicals. Roller skate, chemicals. My jacket, chemicals. This guitar, chemicals. My shoe, chemicals. This watch, chemicals. This fish, chemicals. 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 Me, chemicals. You, chemicals. Ramona, chemicals. No, I said your chemicals. Never mind. This is it. The periodic table of the elements. All matter in the universe is made up of these pure elements. They go together in different ways to make up everything. All matter. Think of it like building blocks. These little atoms are some of the elements on this periodic table. You got
One oxygen, two hydrogen, bam, you got a water molecule. One carbon, two oxygen, hey, it's carbon dioxide. Two carbon, two oxygen, four hydrogen, skadoosh, vinegar. One sodium, one chlorine, hey, that's salt. All matter in the universe is just the stuff on here combining into these. And now, you know your chemicals. Sugar.
Let's take a closer look at what's going on when we mix vinegar and baking soda. All chemicals are made of atoms. There's only 4 types in our reaction: carbon, oxygen, hydrogen, and sodium. When they go together like this is a molecule of vinegar, or acetic acid. And this is a molecule of baking soda, or sodium bicarbonate. When chemicals react, they switch atoms. That one goes there, this one goes over here, and then this one turns into this, and then what you end up with are new molecules. This one is called sodium acetate, and this one is carbon dioxide gas, the gas you breathe out. And do you recognize this one? Right, water, H2O. Why all this happens gets complicated, but the study of chemistry is all about how molecules are built and react with other molecules.
All right, Talina, you ready?
Yep.
You're gonna pour all your baking soda in the fish tank, and I'm gonna pour the vinegar into this bucket, because you don't wanna pour them together right away. Okay, you ready?
Yep.
Okay, go for it. When you're doing your PhD in chemistry, do you get to do stuff like this?
Yeah.
Really?
Got to do a lot of fun reactions in the lab.
Oh, I'm jealous. Have you ever done this much vinegar and baking soda in one time?
I can't say I ever have.
There you go. That's what I like to hear. I already put the soap in the bucket so it would mix with the vinegar when I poured it in. Are you done your baking soda already?
I am.
I'll pour faster. Oh, faster.
It smells vinegary.
It smells vinegar. It makes me want French fries. Okay, Talina, you take this very full bucket of vinegar and dish soap.
Thank you.
I will take this one. Uh-oh, we still have our third bucket. Okay, I'll do these both at the same time. Okay, ready? On the count of 3. 1, 2, 3. Whoa! 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 Wow.
Okay.
That's awesome. So the one thing it didn't do, it didn't shoot up in the air though.
Yeah, it's because the top is quite open, so you would need to constrict it to get it to shoot up.
Oh, yeah, because we're using just sort of a square, a rectangular prism container. We should get something that's maybe something more like our vinegar bottle, right? Because there's lots of space down here, but then it forces it into a tighter opening at the top there, like a volcano.
Yep.
And what else can we do to make it even more powerful, to max it out?
Vinegar is only 5% acid, the rest is water, so you could try using 100%.
So what kind of acid is vinegar?
It's acetic acid.
So vinegar is actually only 5% acetic acid and 95% water. So you can get 100% acetic acid?
Yeah.
Can you get 100% acetic acid?
Yes.
Awesome. Why don't we get a container that's sort of shaped like a funnel, like a volcano,
Yeah.
and 100% acetic acid, and we'll do it again.
Sounds good.
All right, let's do it.
Our vinegar and baking soda reaction went pretty well. But now we're gonna try it with a much stronger type of the same kind of acid you find in vinegar.
Carefully putting this down. And watch out for the baking soda. You never know when it'll get out. And, well, I guess that's just baking soda, huh?
Yeah, that's pretty safe.
Yeah, okay, good. So this is baking soda vinegar volcano version 2. We have this differently shaped glass. What do you call this again?
That's an Erlenmeyer flask.
Why is it called that?
It's actually named after a scientist.
Did he look like that? Was he sort of shaped like this?
No.
No? Was he just a good chemist?
Good scientist, and I think he designed the glass.
Oh, see, there you go. So if you want to have a glass named after you, be a good chemist and design a glass. I want to make a fill beaker. So this is 100% acetic acid.
Yep.
And what's the difference between this and vinegar?
Vinegar